Hello there and welcome to Physics with William, where we take our time with the parts of physics that sound impossible at first, work out what scientists actually mean by them, and see whether the universe is really as peculiar as the names in the textbooks sometimes make it appear. Tonight, we are looking at a substance with one of the most suspicious names in modern physics, strange matter. It sounds like something you would expect to find leaking from a damaged spaceship, stored behind several locked laboratory doors, or quietly growing in the back of a refrigerator after everyone has agreed not to identify it. The real idea is less dramatic, although once you understand what physicists are proposing, it becomes considerably more interesting. Strange matter is a hypothetical form of matter involving some of the same fundamental particles that already exist throughout nature, but arranged under conditions so extreme that the familiar structure of atoms, nuclei, protons and neutrons may no longer be the best way to describe what is there. There is nothing supernatural hiding in the word strange. In particle physics, strange is simply the name attached to one particular kind of quark. What makes the subject remarkable is the possibility that when enough of these quarks appear, alongside the quarks found in ordinary matter, the resulting material might settle into an unusually stable state. It is an idea with a very large word attached to a very small set of particles, and tonight we're going to find out why anyone thought it was worth taking seriously. Before we get into that, have a look at whatever happens to be around you. Perhaps you're listening in bed with the lights low. Perhaps you're on a sofa, on a train, or somewhere considerably less comfortable, while wondering why you did not choose the sofa. Wherever you are, almost everything you can touch is made from the same basic kind of matter. Your hands, the walls, the glass in a window, the air in the room, the ground beneath the building, and the planet beneath that are all assembled from atoms. We become so accustomed to this fact that it is easy to mistake familiarity for inevitability. Ordinary matter seems normal because it is what we have. But suppose you could take the material around you and keep compressing it far beyond anything that happens naturally on Earth. Suppose atoms could no longer keep their normal structure. Nuclei were pushed into direct contact, and even protons and neutrons eventually stopped behaving as separate little packages. What would matter become then? Would it simply be a denser version of what we already know? Or could the ingredients reorganize themselves into something fundamentally different? If you would like, let me know where in the world you're listening from tonight, and what ordinary object is closest to you right now. It might be a pillow, a cup, a lamp, or a phone. Whatever it is, it gives us a useful starting point, because by the end of this journey, we will have followed the matter inside that object, down through several layers of structure, and into conditions where almost none of its familiar properties survive. And if these slower trips through physics help you relax or simply give your mind something interesting to follow at the end of the day, you can leave the video a like and subscribe. It helps this quiet corner of science find a few more curious people, which seems fair considering how much trouble the universe went through to provide us with things to be curious about. To understand strange matter, we first need to be clear about what ordinary matter actually is. An atom consists of a small central nucleus surrounded by electrons. The nucleus contains protons and neutrons, and for many everyday purposes that is far enough to go. Chemistry can build an extraordinary world using those pieces. Change the number of protons and you change the element. Arrange atoms differently, and carbon can become graphite, diamond, or part of a living cell. Combine elements in different ways and you can make water, stone, wood, plastic, chocolate, or whatever substance is responsible for the inside of a cheap sofa cushion. Yet protons and neutrons are not fundamental. Look inside them, and another layer appears. They are made from particles called quarks, and the ordinary nuclear matter around us relies mainly on two types, known as up quarks and down quarks. A proton contains a particular combination of them, while a neutron contains another. The quarks are bound together by the strong interaction, an interaction so effective at keeping them confined that isolated quarks are not found wandering around under normal conditions. Quarks come in more varieties than the two needed to build everyday nuclei. One of those additional varieties is the strange quark. The name comes from the history of particle physics, when researchers discovered particles that behaved in unexpected ways and seemed to live longer than certain simple expectations suggested. Scientists introduced a property called strangeness as part of the system used to classify what they were observing, and the name eventually became attached to one of the quark types. So a strange quark is not strange because physicists ran out of respectable adjectives. It belongs to a well-defined family of elementary particles. It is heavier than an up quark or a down quark, and it can appear in unstable particles produced naturally in high-energy processes or created in particle experiments. What it does not normally do is remain as a major permanent ingredient of the stable matter sitting around your house. By the time matter has settled into the ordinary forms we know, strange quarks are not required to build its nuclei. That makes the central proposal sound odd at first. If strange quarks are heavier than the quarks inside normal protons and neutrons, why would matter containing large numbers of them ever be especially stable? It seems as though adding heavier ingredients should make matters worse rather than better. The answer comes from the fact that the energy of a huge collection of quantum particles depends on more than the mass of each individual ingredient. It also depends on how all of those particles are allowed to arrange themselves. Imagine that a large group of people is trying to find seats in a hall, but only 2 sections are open. As those sections fill, the remaining people are forced into increasingly inconvenient places. Then a 3rd section becomes available. Reaching it may require a little extra effort, but opening those additional seats can allow the crowd as a whole to distribute itself more comfortably. That is not a perfect description of quark matter, but it points toward the basic reasoning. Under enormous densities, providing another available type of quark can change the way the particles share the available quantum states. The strange quark carries an extra cost because it is heavier, but in some theoretical descriptions the broader rearrangement can compensate for that cost. This is where the strange matter hypothesis begins. If matter becomes dense enough for quarks to behave collectively rather than remaining locked into separate protons and neutrons, physicists can ask what mixture of quarks produces the most favourable state. A mixture containing up quarks, down quarks, and strange quarks may, under some assumptions, have a lower energy than a comparable state without the strange quarks. In the most ambitious version of the idea, a sufficiently large amount of strange quark matter could even be more stable than ordinary nuclear matter. That does not mean physicists have discovered such a substance and placed it in a cupboard somewhere. It means our theories of the strong interaction leave open a region in which that possibility has been investigated seriously. Whether nature actually chooses that option is one of the questions we are trying to answer. The distinction between possibility and discovery is particularly important here because strange matter has acquired a rather dramatic reputation outside specialist physics. You may have encountered descriptions suggesting that it is a confirmed substance capable of transforming anything it touches. That skips several very important steps. We do not currently know that stable strange quark matter exists at all. We know strange quarks exist. We know quarks make up protons and neutrons. We know matter can enter unfamiliar phases when temperature and density become extreme. We also have a theory describing the strong interaction between quarks. What remains uncertain is exactly how that theory behaves in some of the densest, relatively cold forms of matter found in nature. Those conditions are especially difficult to calculate, which leaves room for several possible arrangements of dense matter, rather than one universally accepted answer. There is a useful lesson hiding in that uncertainty. When physicists use the word matter, they do not mean one permanent arrangement that nature has agreed never to change. Matter can have phases. Water gives us the easiest example. Ice, liquid water, and water vapour are made from the same molecules, yet their large-scale properties are completely different because temperature and pressure change the way those molecules behave together. A block of ice can support weight. Water flows. Vapour spreads through a room. No new fundamental ingredient is required to move between those forms. The same particles simply organise themselves differently. Nuclear and particle physics allow far more extreme versions of this idea. Change density and temperature enough, and matter can reorganize on scales much smaller than molecules. At sufficiently high temperatures or densities, the boundaries that normally keep quarks associated with individual protons and neutrons can become less meaningful, creating forms of quark matter in which the quarks participate in a larger collective state. This is why the phrase strange matter does not mean ordinary matter sprinkled with a few unusual particles. It refers to a proposed bulk phase. If such matter exists in the traditional picture, strange quarks would be part of the material in large numbers, together with up and down quarks. Instead of having a nucleus containing clearly identifiable protons and neutrons, you would have a collective population of quarks. The individual ingredients are familiar to particle physics, but the organization would be very different from anything you could hold under normal terrestrial conditions. You could not make it by putting enough pressure on a kitchen table, no matter how determined you were or how poor the table's construction happened to be. The pressures involved belong to environments where matter itself is being pushed toward its limits. Another important idea is that stable does not always mean what it seems to mean in everyday conversation. We often call something stable if it sits still and does not appear to change. In physics, we may be asking a deeper question about whether there is another state available with lower energy. Something can survive for an extremely long time even if a lower energy arrangement exists, provided there is a sufficiently difficult barrier preventing the transition. Diamond offers a familiar comparison. Diamond does not instantly turn into graphite while someone is wearing it, even though graphite is the more stable form of carbon under ordinary conditions. The transition is simply not easy enough to occur at an appreciable rate. Nature contains many situations where a state persists not because no alternative exists, but because getting from one state to another is extraordinarily difficult. That matters when people hear the claim that strange matter might be more stable than ordinary nuclear matter, and immediately wonder why the entire universe has not already become strange matter. If strange matter really were the lowest energy bulk form of quark matter, ordinary nuclei could still persist because transforming them would not necessarily be simple. The quarks inside ordinary nuclei cannot merely rearrange their seating plan and announce that they are finished. Producing a significant strange component requires changes in quark type through the weak interaction, and the behavior of a tiny object can differ from that of a large amount of bulk matter, because surfaces, electric charge, and quantum effects become important. The fact that a hypothetical large state might be favourable does not imply that every proton in your body is one minor inconvenience away from turning into something else. That does not make the idea less interesting. In some ways, it makes it more interesting, because it introduces the possibility that the universe could contain matter with two very different kinds of stability. Ordinary nuclei could remain effectively secure under the conditions found on planets and in normal stars, while another arrangement might become favourable only after matter has been compressed beyond an enormous threshold. The difference would not be visible in everyday chemistry. You could live your entire life surrounded by ordinary atoms without ever encountering the conditions needed to reveal the deeper possibility. It would be rather like spending your whole life near sea level and concluding that water could never behave differently because you had never changed the pressure or temperature enough to see another phase. The hardest part is finding out whether that other phase is actually there. Particle accelerators can create extremely energetic collisions and briefly produce forms of matter in which quarks and gluons are not confined in the ordinary way. Those experiments are invaluable for understanding the strong interaction, but the conditions they create are extremely hot and last for tiny fractions of a second. The strange matter hypothesis is often concerned with a different regime, matter that is extraordinarily dense but comparatively cold and capable of persisting for much longer. Reproducing that combination in a laboratory is another matter entirely. We cannot place a few tons of material in a machine, squeeze it until protons overlap, and leave it there while someone goes for lunch. Nature, however, owns better equipment. It has gravity. Given enough mass, gravity can apply pressure on a scale no laboratory apparatus can match. Most of the time, gravity seems remarkably weak. You can lift a book against the gravitational pull of the entire Earth using one arm, which is not much of an advertisement for a fundamental interaction. But gravity accumulates. Every piece of mass attracts every other piece of mass, and in an object as enormous as a star, that accumulation becomes decisive. A normal star spends much of its life balancing gravity against the pressure produced by the hot material and reactions inside it. When that balance fails in the right kind of massive star, gravity can crush the central material to astonishing densities. That is the direction we eventually have to go if we want strange matter to become more than an interesting possibility on paper. Before reaching those objects, though, it is worth noticing how many familiar layers of matter must disappear along the way. Start with an ordinary solid, compress it enough, and the distances between atoms change. Push much further and electrons no longer behave as they do in ordinary chemistry. Keep going, and matter enters regimes where the structure of atoms ceases to be useful. Continue still further, and the distinction between individual atomic nuclei begins to break down. By then, you have left behind almost everything that makes matter recognizable in daily life. Color, texture, hardness, transparency, melting point, and chemical identity have become side issues. The important questions involve pressure, density, quantum states, particle populations, and which interactions allow the material to resist further compression. At some stage, even the familiar picture of separate neutrons and protons may become inadequate. A proton has a definite identity when it's comfortably separated from neighbouring particles. Pack huge numbers of them and neutrons together at tremendous density, and their constituent quarks are brought into a very different environment. The strong interaction that normally confines those quarks is still there, but the most useful state of matter may change. Instead of thinking about a collection of individual bags, each containing 3 quarks, physicists consider whether the quarks could become deconfined and participate in a shared state extending across a much larger volume. Once that door opens, the question of which quark varieties are present becomes unavoidable. Up and down quarks are the natural starting ingredients, because ordinary neutrons and protons already contain them. Strange quarks enter because at sufficiently high density, the energy balance can make their appearance favourable. The result is the proposal behind strange quark matter, a dense phase containing all 3 of those quark types in substantial numbers. Exactly how many of each type would appear depends on the state of the material and the interactions involved. The simple picture of 3 comparable populations is useful, but real calculations have to take account of particle masses, electric charge, interactions between quarks, and the requirement that the material settle into equilibrium. The deeper physicists go into the problem, the less it resembles a box filled with 3 colours of marbles, and the more it becomes a difficult many-particle problem governed by the strong interaction. That strong interaction is one reason strange matter remains such a stubborn question. The theory behind it is called quantum chromodynamics, and it successfully describes the interactions of quarks and gluons. Calling the theory successful does not mean every possible calculation becomes straightforward. Some physical regimes are much easier to handle than others. Matter at extremely high density and relatively low temperature presents serious theoretical challenges. Different models can produce different predictions about when deconfined quark matter appears, whether strange quarks become abundant, and whether the resulting state would be more stable than ordinary nuclear matter. It is possible for scientists to agree completely on the underlying theory, while still debating what that theory predicts in a particular extreme situation, because the mathematics needed to extract the answer is exceptionally difficult. There is also more than one candidate for what ultra-dense matter might become. It may remain largely in a form describable using neutrons, protons, and additional particles. It may undergo transitions to more exotic nuclear states. It may develop regions of deconfined quarks. Those quarks may form highly organized paired states of their own. Strange quarks may become important, or another composition may be preferred. Some recent theoretical work has even emphasized that stable quark matter need not necessarily be strange in the traditional sense. That possibility is a useful reminder not to become too attached to a compelling name. Nature has no obligation to select the option that gives a documentary the best title. So when we ask what strange matter really is, the most accurate answer at this stage is not that it is a discovered substance with a known list of properties. It is a proposed form of dense quark matter that may become favourable under extreme conditions, with strange quarks playing a major role in its composition. The strongest version of the strange matter hypothesis goes further and asks whether this material could be absolutely stable in bulk. That possibility has remarkable consequences, but it remains a possibility rather than an established fact. No confirmed piece of stable strange matter has been placed on a laboratory scale. Searches for small hypothetical fragments have not given us a definitive detection, and astrophysical observations have not yet provided an answer everyone accepts. That leaves us in a useful position. We have enough established physics to understand why the idea arose, but not enough evidence to know whether nature actually uses it. We know that protons and neutrons have quarks inside them. We know strange quarks are real. We know extreme conditions can alter the collective state of matter. We know gravity can create densities far beyond those found in planets and ordinary stars. What we need is somewhere all of those facts meet. The universe supplies exactly such places after certain stars die. A massive star can spend millions of years supporting itself against gravity, building heavier elements in its interior, and maintaining a balance that looks impressively permanent right up until it is not. When the central support eventually fails, the collapse can force an enormous amount of matter into a remarkably small region. The resulting object can contain more mass than the Sun, while measuring roughly the size of a city. At those densities, atoms are long gone. The material is no longer behaving like anything in a laboratory sample. Pressure reaches levels where the properties of individual particles determine the structure of an entire star, and the deeper you move toward the centre, the less certain our description becomes. These objects are neutron stars, although the name can give the misleading impression that their interiors are simply giant collections of neutrons and nothing more. Their outer regions are already complicated, and their deepest interiors may contain forms of matter we have never directly observed. That is where the strange matter question becomes physical rather than merely hypothetical. If the pressure rises enough to break down the familiar organization of protons and neutrons, their quarks could begin participating in a new collective state. If strange quarks lower the energy of that state, they may appear in abundance. If strange quark matter is sufficiently stable, it might occupy a central region or, under more dramatic possibilities, determine the nature of the entire compact object. Before we can decide whether any of that is plausible, we need to understand what a neutron star actually does to matter as we move from its surface toward its centre. The journey is not simply a matter of squeezing the same substance harder and harder. At each increase in density, nature gets another opportunity to rearrange the available particles. Electrons behave differently. Nuclei become increasingly neutron-rich. Free neutrons appear. Nuclear boundaries become less distinct. New particle species may become energetically possible. Eventually, the idea of a neutron or proton itself may have to compete with a description written directly in terms of quarks. That is where the comfortable matter around us finally stops being a useful guide. The object closest to you right now is held together by forces and structures that work beautifully at ordinary density. Its atoms have room. Its nuclei are isolated from one another. Its protons and neutrons can maintain familiar identities. None of those conveniences survive indefinitely under compression. Deep inside a compact star, gravity does not care whether matter finds the situation comfortable. It keeps pushing until quantum physics and the fundamental interactions produce enough resistance to stop it, or until nothing can stop collapse at all. To find strange matter, then, we do not begin by searching for something strange. We begin with perfectly ordinary matter and ask what remains of it when gravity removes one familiar layer after another. That brings us to the crushed hearts of neutron stars, where a spoonful is no longer a sensible unit of comparison. Atoms are a distant memory, and the question of what matter really wants to become can no longer be answered by looking at anything here on Earth. A neutron star begins with something much more familiar, a star that has spent millions of years holding itself together through a balance between gravity pulling inward and pressure pushing outward. For most of its life, that arrangement works remarkably well. Nuclear reactions in the interior provide energy. The hot material resists compression, and gravity is prevented from simply dragging everything toward the center. Eventually, however, a sufficiently massive star reaches a point where the central regions can no longer maintain that balance. The details depend on the star and its history, but the important part for us is what happens next. The core collapses. Matter that was once spread through an enormous stellar interior is driven inward with extraordinary force, and the familiar architecture of atoms begins to fail. Electrons can no longer remain comfortably separated from nuclei. The density climbs into a regime unlike anything found naturally on Earth, and the collapsing material is transformed into the compact object we call a neutron star. The name sounds simple. The object is anything but simple. If you could somehow approach one without being destroyed by the surrounding radiation, magnetic fields and gravity, the first surprise would be how little space contains so much mass. A neutron star can contain an amount of matter comparable to or greater than the mass of the Sun, while occupying a region only about the size of a city. This is not simply ordinary material pressed together more tightly, like clothing packed into an over-enthusiastic suitcase. Compression on this scale changes which forms of matter are possible in the first place. The pressure is so enormous that the internal structure becomes layered, with different particle arrangements favoured at different depths. Even the crust, which sounds rather reassuringly solid, is nothing like the crust beneath your feet. Models of neutron star crusts describe a progression from a lattice of extremely neutron-rich nuclei and electrons in the outer layers to an inner region where neutrons are no longer all confined inside nuclei. It helps to imagine descending through the star, although descending is a dangerous word when gravity is this strong. Near the surface, matter is already compressed far beyond normal solids. Atoms cannot preserve their usual electron clouds. The pressure forces electrons into states that would never be occupied in an ordinary piece of material. The nuclei themselves arrange into a crystalline lattice, while electrons move through the material more freely. You might call this a solid, but only in the broad sense that there is an ordered structure capable of resisting shear. It would bear almost no resemblance to stone, metal, ice, or any other solid you have handled. If someone handed you a piece of neutron star crust, the more immediate problem would be that they had somehow handed you a piece of neutron star crust, and questions about texture could probably wait. Going deeper increases the pressure, and something interesting happens to the nuclei. They become increasingly rich in neutrons. Under normal conditions, atomic nuclei contain some balance between protons and neutrons that allows them to remain bound. Add too many neutrons to an ordinary nucleus, and it eventually becomes unstable. Inside a neutron star, however, the surrounding pressure and the sea of energetic electrons change the situation. Reactions can convert protons and electrons into neutrons, producing nuclei that would not survive as ordinary atoms in a laboratory. The deeper you go, the more neutron-rich those nuclei become. Eventually they reach a point where some neutrons are no longer bound inside individual nuclei at all. They begin to leak out into the space between them, creating what physicists call the neutron drip region. It is a wonderfully ordinary-sounding phrase for a situation involving matter compressed to hundreds of billions of times the density of water. Once neutron drip has occurred, the material enters the inner crust. There are still nuclei arranged in a lattice, and there are still electrons, but now there is also a background of unbound neutrons moving through the structure. These neutrons can behave collectively in a quantum state known as a superfluid. A superfluid is not simply an especially runny liquid. It is a state in which huge numbers of particles participate in coordinated quantum behavior. In terrestrial laboratories, superfluidity produces effects that seem almost mischievous, such as fluid moving with extremely little resistance. In neutron stars, neutron superfluidity can influence how the star rotates, how it exchanges angular momentum between different internal regions, and possibly how sudden changes in rotation occur. The crust is therefore not merely a shell sitting passively around the star. It participates in some of the most interesting behavior astronomers can observe. The deeper parts of the inner crust may become stranger still before we have even reached strange matter. As nuclei are squeezed closer together, the competition between the attractive nuclear interaction and electric repulsion can favour unusual shapes. Instead of remaining roughly spherical, nuclear structures may stretch into rods, flatten into sheets, or form more complicated arrangements. Physicists often refer to these possible configurations as nuclear pasta, because some of the predicted shapes resemble varieties of pasta. This is one of those rare occasions when the scientific nickname is actually easier to remember than the formal description, although it does create the odd situation in which a serious conversation about dead stars may include references to spaghetti and lasagna. The important point is not the resemblance to dinner. It is that matter is already reorganizing itself because the familiar structure of isolated nuclei is becoming increasingly difficult to maintain. Eventually, the distinction between the inner crust and the core is reached. The individual nuclear structures disappear, leaving matter that is much more uniform. We are now inside the region that makes up most of the star. Despite the name neutron star, this material is not expected to consist entirely of neutrons. Neutrons dominate, but some protons remain, and electrons are needed to maintain electrical neutrality. Muons can also appear once the conditions make them energetically favourable. The relative amounts are determined by a balance between the weak interaction, electric charge, pressure, and quantum statistics. At this depth, the matter is better pictured as an extraordinary quantum liquid than as a pile of tiny hard balls. The particles are packed so closely that their collective behaviour matters as much as their individual identities. Neutrons in the core are widely expected to exhibit superfluid behaviour under appropriate conditions, while protons may form a superconducting state. The possibility of a superconducting neutron star core has important consequences for the star's magnetic field, because superconductors interact with magnetic flux in ways that ordinary conducting matter does not. Research into neutron star interiors therefore has to connect phenomena that, in terrestrial physics, might belong to completely different laboratory specialties. Nuclear physics determines how particles interact. Condensed matter ideas help describe superfluidity and superconductivity. General relativity determines the structure of the entire star. Astronomy provides the observations. A neutron star does not care that universities put these subjects in separate departments. As we continue inward, however, certainty begins to fade. The outer layers can be modelled with considerable confidence because the densities, while extraordinary, connect more directly to nuclear physics that can be constrained by experiments and established theory. The central core is harder. There, matter may reach several times the characteristic density found inside ordinary atomic nuclei. We cannot simply reproduce a star-sized sample of such material on Earth and measure its properties directly. Instead, physicists construct theoretical descriptions of dense matter and ask which ones remain compatible with astronomical observations. This relationship between pressure and density is often discussed through what physicists call the equation of state. We will not need the mathematics here. Conceptually, it tells us how resistant a particular form of matter is to compression. That resistance is crucial because gravity is trying to compress the star while the internal matter is trying to resist. If the material is relatively easy to compress, the star can become smaller for a given mass. If it resists strongly, the star can remain larger. The internal composition therefore leaves clues in observable properties, such as stellar masses and radii. This sounds simple until you remember that neutron stars are distant objects roughly the size of cities, surrounded by intense gravity, often rotating rapidly, and generally unwilling to allow astronomers to place measuring tape around them. Extracting the properties of their interiors from observations requires careful modelling, and different descriptions of dense matter can sometimes reproduce similar external behaviour. Still, one fact has already proved extremely useful. We know that neutron stars with masses around twice that of the Sun exist. Any proposed form of matter for the interior must therefore be capable of supporting stars at least that massive. If a theoretical model makes dense matter too easy to compress, gravity wins too soon, and the model fails to support the observed objects. This simple observational requirement has ruled out or constrained many proposed descriptions of neutron star interiors. It does not tell us exactly what the core contains, but it narrows the field. Nature has effectively performed the experiment for us, and astronomers are trying to read the result from very far away. The possibilities become more exotic as density rises. One option is that the matter remains primarily composed of neutrons, protons, electrons, and related particles all the way toward the centre. Another is that additional types of strongly interacting particles appear. Particles containing strange quarks, known collectively in some contexts as hyperons, may become favourable once the available energy is high enough. Their appearance would introduce strangeness into the star, without requiring the complete dissolution of protons and neutrons into bulk quark matter. This creates an interesting complication. Finding evidence that strange quarks matter inside a neutron star would not automatically prove that strange quark matter exists. Strange quarks can enter the story in more than one way. There is a catch with adding new particle species. Allowing particles to rearrange themselves into additional states can lower certain contributions to the energy, but it can also make the material less resistant to compression. If the core becomes too soft, it may struggle to support the heavy neutron stars we know exist. This tension has produced long-running debates about which exotic particles can appear, how strongly they interact, and whether additional repulsive effects could keep the material sufficiently stiff. Neutron star physics repeatedly returns to this balancing act. A proposed phase must make microscopic sense and also support the enormous weight of the star above it. At greater density, the question becomes more fundamental. Protons and neutrons are themselves made from quarks. A neutron contains up and down quarks bound together by the strong interaction, as does a proton in a different combination. Under ordinary conditions, those quarks remain confined. Even inside atomic nuclei, it is usually useful to talk about identifiable protons and neutrons rather than one shared pool of quarks. But there is no guarantee that this description remains valid indefinitely as the particles are forced closer together. At some sufficiently extreme density, the boundaries separating neighbouring nucleons may cease to be the best way to describe the system. Imagine a crowded gathering where everyone has been told to remain inside separate circles drawn on the floor. At first, the circles are far apart and the arrangement is easy. Move the circles closer and people become uncomfortable, but can still tell which group they belong to. Continue shrinking the available space, and eventually the idea of separate groups becomes more trouble than it is worth. At that point, describing one large crowd may be more useful than insisting that every person still belongs to an isolated circle. Dense nuclear matter may face an analogous change of description. Protons and neutrons are not literal containers with hard walls, but their quark structures begin to overlap more strongly as density increases, and a description involving deconfined quark degrees of freedom may eventually become appropriate. Whether this change happens sharply or gradually is one of the major uncertainties in dense matter physics. Some models describe a phase transition where nuclear matter gives way to quark matter once particular conditions are reached. other approaches allow a smoother crossover in which the character of the matter evolves continuously from hadronic behavior toward quark behavior. There may even be an intermediate region where descriptions in terms of nucleons and descriptions in terms of quarks overlap in usefulness. The strong interaction does not have to arrange its phases according to the tidy labels humans prefer to place on diagrams. If deconfined quark matter does appear in the core, it need not immediately be the strange matter we are ultimately interested in. The first quark phase could be dominated by up and down quarks. Strange quarks might appear only at greater density. Different forms of quark pairing may develop. There could be mixed phases, where regions with different compositions coexist, depending on the surface effects and electrical properties. Theoretical work on neutron star interiors has explored many such possibilities, and models of quark deconfinement continue to treat the transition as dependent on the uncertain behavior of strongly interacting matter at high density. This uncertainty is exactly why neutron stars are so valuable. They force microscopic particle physics to reveal itself through macroscopic objects. A tiny change in how particles interact at distances far smaller than an atomic nucleus can alter the pressure throughout the stellar core. That changes how much gravity the star can support, which changes the relationship between its mass and size. It can influence how the star cools because different particles carry and release energy differently. It can affect rotational behavior, magnetic properties, and what happens when two neutron stars collide. The core may be hidden beneath kilometers of material, but it is not completely silent. Cooling offers one example. A newborn neutron star begins extremely hot and loses energy over time, primarily through elusive particles called neutrinos during much of its early thermal evolution, and later through radiation from the surface. The rate of cooling depends on which reactions are available inside the star. Change the composition and you may open or close efficient channels for carrying energy away. Superfluidity changes the story again because paired particles participate differently in reactions. Exotic particles or quark matter could introduce additional processes. Astronomers therefore compare observed surface temperatures with theoretical cooling histories in an attempt to learn what may be happening far beneath the surface. Rotation provides another window. Many neutron stars are observed as pulsars because beams of radiation sweep past Earth as the star rotates, producing remarkably regular pulses. Some pulsars suddenly increase their rotation rate in events known as glitches. These changes are tiny compared with the total rotation of the star, but their timing and magnitude provide clues about how angular momentum is stored and transferred internally. Superfluid neutrons in the crust and perhaps deeper regions are believed to play an important role. A star whose interior contains multiple quantum fluids, superconducting components, and possibly exotic central phases is not merely a dense ball. It is a coupled system in which different components can move and respond on different timescales. Then there are neutron star collisions. When two neutron stars spiral together and merge, they generate gravitational waves that carry information about how easily the stars deform under one another's gravity. That deformability depends on the properties of dense matter. The merger also compresses and heats the material further, potentially creating conditions different from those in an isolated cold neutron star. For a brief period, the combined object can become a laboratory for nuclear and particle physics at extremes we cannot reproduce elsewhere. Whether quark matter appears during such events, and whether a transition leaves an observable imprint in gravitational waves or electromagnetic signals, is now a serious area of research rather than a purely theoretical exercise. All of these clues are valuable because we cannot look directly into the centre. There is no telescope setting marked core. Light from the surface tells us about the exterior. Gravitational waves reveal aspects of the star's bulk response. Pulsar timing tells us about rotation. Mass measurements tell us how much weight the internal matter can support. Each observation gives a different constraint, and physicists combine them like pieces of a puzzle, whose central image remains hidden. The result is an unusual situation in science. We know the broad journey through a neutron star reasonably well, especially through its outer regions, but the deepest few kilometers may contain an entirely different phase of matter. A small change in depth can correspond to an enormous change in pressure. A material that is energetically unfavourable slightly farther out might suddenly become preferred nearer the centre. New particles can appear because the system is always searching for the most favourable way to distribute its enormous density while obeying the conservation laws and interactions of particle physics. This is where the strange quark begins to move from being an optional curiosity toward becoming a potential participant. Strange quarks are heavier than the up and down quarks that dominate ordinary nuclear matter, so producing them requires an energy cost. In normal conditions, that cost makes them temporary visitors. Inside a sufficiently compressed core, however, the situation changes. The available quantum states for neutrons, protons, and their constituent quarks become increasingly crowded. Introducing additional particle species can allow the system to rearrange itself. The question is no longer whether a strange quark is heavier in isolation. It is whether a huge collection of matter can lower its total energy by allowing some of its up and down content to change into strange content. There is a useful distinction here between pressure forcing something to happen and pressure making something possible. Gravity does not reach into a proton and mechanically pull the quarks apart. Instead, gravity compresses enormous quantities of matter. That compression changes the density and therefore the energetic balance among the states available to the particles. When a new state becomes favourable, the interactions of particle physics handle the rearrangement. Gravity builds the room. Quantum physics decides how everyone sits. Near the centre of the most massive neutron stars, this competition may become intense enough that the identity of protons and neutrons itself begins to lose its privileged status. If quarks can occupy a lower energy collective arrangement than confined nucleons under those conditions, matter may undergo a transition. The exact density at which this might happen is not known with confidence, and it may not happen in every neutron star. A lighter neutron star could have central pressure too low to reach the necessary regime, while a more massive one might cross it. Two objects that look broadly similar from the outside could therefore hide different internal compositions. That gives us a particularly interesting possibility. The universe may contain neutron stars whose cores are entirely nuclear, others with small regions of quark matter, and perhaps still others whose interiors have undergone much more extensive reorganization. The word neutron star would then describe a family of compact objects rather than a guarantee about every particle inside them. Astronomers already use the name in that broader practical sense because the interior composition remains uncertain. Some hypothetical objects go even further. If strange quark matter were absolutely stable, a compact star might be converted largely or entirely into that phase and would be more accurately described as a strange star. Such an object could resemble a neutron star in many external respects, while possessing a radically different microscopic interior. But we're not ready to make that leap yet. Before a whole star can become strange matter, we need to understand the smaller and more immediate question of how the particles we already know could stop behaving like the protons and neutrons we recognize. That transition is subtle, because a proton does not suddenly acquire a visible crack down the middle when the pressure becomes high enough. Quarks are quantum objects, and confinement is a property of the strong interaction rather than a physical shell surrounding each nucleon. To understand how the familiar particles might give way to a collective quark state, we have to look more closely at what confinement means, why individual quarks are normally trapped inside hadrons, and what changes when enormous numbers of those hadrons are pushed so close together that their internal structures can no longer ignore one another. Deep beneath the crust in the neutron-rich fluid, this is where the next transformation may begin, as protons and neutrons stop being the final pieces of the picture, and the quarks inside them become impossible to overlook. Deep inside a neutron star, the word dissolve needs a little explanation, because a proton does not dissolve in the same way that sugar disappears into tea. There is no tiny solid proton gradually becoming transparent until only a faint proton flavour remains. Protons and neutrons are quantum objects made from quarks and gluons, and when physicists talk about them dissolving at extreme density, they mean that the familiar boundaries separating one proton or neutron from another may stop being the most useful description of the matter. The ingredients remain. The up quarks are still there, the down quarks are still there, and the strong interaction is still governing their behaviour. What changes is the way those ingredients are organised. At lower density, nature packages quarks into individual particles such as protons and neutrons. At sufficiently high density, those packages may overlap so strongly that describing the material directly in terms of quarks begins to make more sense. Whether this happens through a sudden transition or through a gradual change remains one of the difficult questions in the physics of dense matter, but the basic possibility follows from something we already know about protons and neutrons. They were never indivisible objects to begin with. A proton is made from 3 quarks in the simplest description, 2 up quarks and 1 down quark. A neutron contains 2 down quarks and 1 up quark. That sounds pleasantly tidy, although the real internal structure is considerably busier. The quarks interact by exchanging gluons, and the strong interaction constantly produces a complicated quantum environment containing additional short-lived quark and antiquark contributions. If you could somehow look inside a proton with ordinary eyes, which you cannot, it would not resemble 3 coloured marbles sitting politely in a bag. It is a dynamic quantum system. Still, the 3 main quarks determine important properties of the proton and neutron, and the distinction between those 2 particles comes from the different combination of up and down quarks. This means that when we compress neutron-rich matter, we're ultimately compressing systems whose internal ingredients are already quarks. The question is not where quarks suddenly come from. They were present from the beginning. The question is when their confinement inside separate protons and neutrons ceases to dominate the way the material behaves. Confinement is one of the defining features of the strong interaction. In ordinary conditions, quarks do not appear as isolated particles. You cannot break open a proton, catch one of its quarks, and keep it in a container for later. Trying to separate quarks does not work like separating 2 magnets, or pulling apart pieces of a molecule. The strong interaction behaves in a very different way. As the separation between quarks increases, the energy stored in the strong field between them can grow until it becomes energetically favourable to create new particles rather than leave a single quark isolated. The result is that experiments detect combinations of quarks bound into particles rather than lonely quarks, travelling freely across the laboratory. Nature seems remarkably committed to this arrangement. If quarks were hotel guests, confinement would be the management policy stating that nobody leaves the building alone. The gluons responsible for the strong interaction add another level of complication. They do not merely transmit the interaction between quarks. Unlike photons, which do not carry electric charge, gluons themselves carry the kind of charge associated with the strong interaction, called colour charge. This allows gluons to interact with other gluons, producing a theory whose behaviour is much richer than a simple attraction between particles. The word colour has nothing to do with visible colour. Quarks are not literally red, green, or blue in the ordinary sense, and shining a torch into a proton would not reveal a tasteful selection of primary colours. Colour is simply the name physicists gave to a quantum property needed to describe the strong interaction. Once again, particle physics has chosen terminology that sounds more cheerful than the mathematics underneath it. At the distances and energies relevant to ordinary protons and neutrons, this interaction is strong enough to keep the quarks confined. But the strong interaction has a remarkable property. Under sufficiently extreme conditions involving very short distances or very high energy scales, quarks can behave as though their effective interaction becomes weaker. This feature is known as asymptotic freedom. It does not mean that the strong interaction switches off. nor does it mean that neutron star matter automatically becomes a gas of completely independent quarks. It tells us that the behaviour of the interaction changes with scale. At extraordinarily high density, quarks occupy states with very large characteristic momenta, and descriptions based directly on quarks become increasingly appropriate. In the truly extreme density limit, physicists can calculate important properties of cold quark matter using methods that become more reliable because of this weakening of the effective interaction. The densities inside actual neutron stars are probably not high enough to place their entire cores safely in that simple limit, which is precisely why the region between ordinary nuclear matter and clearly defined high-density quark matter remains difficult. To see why density matters, return to the crowd analogy, but make the room much more uncomfortable. Imagine that every person represents a quantum particle, and that the rules of the building prevent identical people from simply occupying the same state. As more people enter, the easy places fill first. The newcomers have to occupy increasingly energetic positions. No amount of asking them to stand closer solves the problem because quantum mechanics restricts which states are available. This is one reason highly compressed matter develops enormous pressure. The particles are not merely bumping into one another like balls in a box. Quantum rules force them into higher and higher energy states as density increases. Inside a neutron star, this effect operates alongside the interactions between the particles and helps resist gravity. Now imagine that the people in the room are themselves groups of smaller people standing inside tightly defined circles. At modest crowding, each group can preserve its own circle. You can point to one and say that this is group number 1, while the next circle contains group number 2. That resembles the situation in ordinary nuclear matter, where quarks abound into identifiable protons and neutrons. Increase the crowd enough, however, and the circles begin pressing into one another. Eventually, insisting that every smaller person belongs permanently to one isolated circle may become an awkward way to describe what is happening. The entire room has become one densely connected system. This is closer to the idea behind the transition from hadronic matter to quark matter. The quarks do not vanish from one description and reappear in another. The distinction between the individual composite particles becomes less useful. The difficulty is knowing exactly when that happens. A proton is not a hard container with a measurable wall that suddenly cracks at a particular pressure. Its structure is produced by quantum fields and the strong interaction. As neighbouring protons and neutrons are forced closer together, their internal quark and gluon structures increasingly influence one another. There may be no single instant at which someone could place a tiny flag in the star and announce that protons end here and quarks begin 1 millimetre farther down. Some theoretical pictures allow a distinct phase transition, where the character of the matter changes sharply once a certain pressure is reached. Others allow something closer to a crossover, where the material gradually develops more quark-like behaviour without an abrupt boundary. There are even ideas in which aspects of hadronic and quark descriptions coexist across an extended range of density. This is not unusual when physics deals with large collections of particles. The labels we give different phases are useful because they describe dominant behaviour, but nature is not required to provide a clean line every time humans would like one. Consider the difference between a dense crowd and a queue. In one situation, you can clearly say when the queue ends and the crowd begins because there is a gate separating them. In another situation, the queue may simply become less organised, as more people arrive until nobody can agree where it stopped being a queue at all. Dense nuclear matter could, in principle, behave in either sort of way. The challenge is that the underlying strong interaction in this particular regime is difficult to calculate directly enough to settle the question. There is one environment where we already know that quarks and gluons can form deconfined matter. In extremely energetic collisions of heavy atomic nuclei, experiments create a very hot state known as quark-gluon plasma. For a tiny fraction of a second, the conditions become so extreme that quarks and gluons are no longer organised only into ordinary individual hadrons. This does not prove that the cold centres of neutron stars contain quark matter, because the two situations occupy very different parts of the physical landscape. Heavy ion collisions create extraordinarily hot matter for an extraordinarily short time. Neutron star cores are comparatively cold, but incredibly dense, and they can remain that way for astronomical periods. It is rather like proving that water can become vapour, and then asking what it does under enormous pressure near freezing. Knowing one unusual phase exists is helpful, but it does not automatically tell you where every other phase boundary lies. Cold, dense matter is particularly troublesome, because increasing density changes several things at once. The particles are pushed into higher quantum states. The interactions between neighbouring nucleons become increasingly important. New types of particles may become favourable. The internal structures of protons and neutrons begin overlapping more strongly. At the same time, the material must remain electrically balanced and settle into equilibrium under the weak interaction. Every possible arrangement has an energy cost, and nature favours whichever arrangement works best under the conditions available. This means the question of deconfinement cannot be answered simply by asking whether protons physically fit next to one another. Quantum objects do not come with convenient packaging dimensions printed on the side. Suppose, though, that the density continues to increase and quark degrees of freedom become important. At first, you might imagine that the material becomes a simple liquid containing the up and down quarks that were already inside the neutrons and protons. That picture captures part of the idea but misses how strongly quantum mechanics shapes the result. Quarks are fermions, meaning they obey the same broad exclusion principle that governs electrons, protons and neutrons. Identical quarks cannot all settle into exactly the same quantum state. As the density rises, available low-energy states fill up, and additional quarks must occupy higher ones. The matter therefore develops enormous pressure even without imagining the quarks as little objects bouncing around inside a container. Quarks also possess several internal properties that give them more ways to arrange themselves than a simple collection of identical particles would have. They come in different flavours, including up and down, and they carry colour charge. These additional possibilities matter because distributing particles among different available states can change the total energy. The system continually has to balance the cost of creating or maintaining a particular particle type against the advantage of giving the enormous population more ways to organise itself. This is the same general principle that will eventually make strange quarks relevant. Before reaching them, however, even a system containing only up and down quarks can behave in unfamiliar ways. One important possibility is pairing. At sufficiently high density and low temperature, quarks near the relevant energy surface may form correlated pairs. The idea has a distant resemblance to what happens with electrons in an ordinary superconductor, although the interactions and resulting states are different. Because the paired objects carry colour charge, the resulting forms of matter are called colour superconductors. This does not mean a neutron star core becomes a gigantic version of a superconducting wire from a laboratory. The name refers to the underlying quantum organisation. Dense quark matter can potentially support several pairing patterns depending on which quark flavours are present, their relative populations, and the density. Once strange quarks enter in substantial numbers, still more symmetrical pairing arrangements become possible, but that is getting slightly ahead of the matter currently being squeezed. The transition from nucleons to quarks can also change the way pressure responds to density, and that has consequences for the whole star. Remember that the interior must support the weight of everything above it. If the appearance of a new phase causes the matter to become much easier to compress, the star may contract somewhat as its interior rearranges. If the new quark matter develops strong repulsive interactions or pairing effects that make it more resistant, it may still support a very massive star. This connection between microscopic interactions and the size of an astronomical object is one of the reasons dense matter physics is so interesting. A change taking place on scales far smaller than an atomic nucleus can influence whether an object containing more mass than the Sun has a radius a little larger or smaller. A sufficiently strong first-order transition could produce even more dramatic structural effects. In some models, a core of one phase appears inside material of another phase, with a relatively distinct interface between them. As pressure increases, the core can grow. Other models allow a mixed region where different phases coexist over some range. Still others replace the sharp transition with a continuous evolution. Physicists investigate all of these possibilities because current observations do not yet provide one completely unambiguous answer. Mass and radius measurements constrain the possibilities. Gravitational waves from merging neutron stars add information about how easily the objects deform. Cooling and rotational behavior may offer additional clues. But extracting a microscopic phase transition from these signals is difficult because several different internal models can produce similar external observations. There is also a subtle problem with the language we're using. If protons and neutrons gradually lose their separate identities, at what point should we stop calling the material nuclear matter and start calling it quark matter? The answer may depend partly on which description explains the relevant physics most efficiently. Something similar happens in other areas of science. A wave in water can be described by tracking individual molecules, but that is rarely useful. At larger scales, describing the water as a continuous fluid works better. Neither description makes the molecules disappear. One simply becomes more practical. Dense matter may contain a region where both hadronic and quark descriptions capture different aspects of the same underlying system. This possibility is sometimes discussed through the idea of quark-hadron continuity. The broad suggestion is that matter could evolve from a regime naturally described by hadrons into one naturally described by quarks without needing a violent discontinuity between them. Not every theoretical approach agrees that such continuity occurs in the conditions relevant to real neutron stars, and different forms of dense matter may still be separated by genuine phase transitions. What the idea demonstrates is that dissolving does not have to mean exploding, breaking, or suddenly releasing a cloud of free particles. The transformation could be subtle enough that no individual proton experiences a dramatic final moment. Instead, the collective system changes until the proton is no longer the most useful unit for describing it. Think about a busy city seen from different heights. Standing on the pavement, the important objects are individual people and vehicles. From the roof of a tall building, traffic streams become more useful than individual cars. From an aircraft, whole neighbourhoods become patterns. Nothing physically disappears simply because your description changes. In dense matter, however, the change goes deeper because the interactions themselves can reorganize the quantum state. Protons and neutrons are not merely becoming difficult to distinguish from a distance. Their constituent quarks may begin participating in collective states extending across regions larger than any one original nucleon. That brings us to a common misconception. Deconfined quark matter does not necessarily mean quarks are completely free. The word deconfined can sound as though the particles have escaped every interaction and are now drifting independently. In reality, quarks in dense matter can remain strongly interacting. At the densities likely relevant to neutron stars, the strong interaction may still be substantial. The quarks can scatter, pair, and form complicated correlated states. Deconfinement means they are no longer restricted to belonging to separate color-neutral hadrons in the familiar way. It does not mean they have stopped noticing one another. A crowded room without assigned tables is still a crowded room. At fantastically higher densities, well beyond the comfortable reach of neutron star modelling, asymptotic freedom makes the theoretical picture cleaner. There, the interaction becomes weak enough at the relevant scales that calculations can be performed more systematically. This gives physicists an important anchor at the extreme high density end. At lower densities around ordinary nuclear matter, experiments and nuclear theory provide another anchor. Unfortunately, neutron star cores occupy much of the difficult territory between those limits. We understand the shoreline on both sides better than the foggy water in the middle, and the star happens to be sitting somewhere in that fog. Researchers therefore build models designed to connect what is known at lower density with what is known at very high density while remaining compatible with observed neutron stars. Some models predict that quark matter begins to matter relatively early in the core. Others keep nucleons dominant until much greater density. Some permit smooth evolution. Some favour a first-order transition. Current observations have become good enough to eliminate many unrealistic possibilities, but they have not yet forced every viable model into one identical microscopic picture. That uncertainty is not merely a matter of waiting for a slightly better telescope. It reflects the genuine difficulty of strongly interacting quantum matter. Now consider what the matter itself is doing while all this theoretical uncertainty bothers the physicists. Gravity continues compressing it. The low-energy states available to the dominant particles become increasingly crowded. The system searches for ways to lower its energy while maintaining charge balance and equilibrium. If up and down quarks have begun to participate directly in the dense state, the next question is unavoidable. Are those two flavors enough? At ordinary density, the answer appears to be yes for stable nuclei. Up and down quarks build the protons and neutrons, and chemistry gets on perfectly well from there. But inside sufficiently dense quark matter, limiting the system to only two major quark flavors can become energetically expensive. There are enormous numbers of quarks occupying available quantum states, and each flavor has its own set of states to fill. Adding another flavor would provide an additional set of possibilities. The obvious difficulty is that the next available quark flavor is heavier. Creating it costs energy. Under ordinary conditions, that cost wins immediately, which is why your body does not contain stable nuclei filled with strange quarks. Dense matter changes the calculation. When the up and down quark populations are pushed into sufficiently energetic states, replacing some of them with a heavier quark can become competitive because the new flavor opens additional lower-lying states that were previously unavailable to the system. It is the quantum version of discovering another room after the first two have become unbearably crowded. The new room may be upstairs and slightly inconvenient to reach, but eventually the crowding downstairs makes the journey worthwhile. There is another route into the same idea. Weak interactions can change quark flavor. A down quark can participate in processes that produce a strange quark when the energy conditions allow it, and the reverse can also occur. In ordinary environments, the strange quark is too heavy for a stable population to remain favourable. In sufficiently compressed matter, chemical equilibrium may instead demand that strange quarks appear. Once that threshold is crossed, strangeness stops being merely a temporary feature of short-lived particles and becomes a possible component of bulk matter. This is the point where the story changes character. Until now, everything could be understood as taking ordinary nuclear matter and squeezing it until the proton and neutron labels begin to lose their usefulness. The ingredients were still mainly the familiar up and down quarks. But the dense system does not care which particles happen to be common in kitchens, oceans, or planets. It cares about the total energy allowed by the fundamental interactions. If introducing a heavier quark species lowers that total energy under extreme compression, then being heavier is no longer enough to keep it out. The strange quark, therefore, does not enter because the universe suddenly becomes exotic for the sake of variety. It enters for the same practical reason any new particle species can appear in dense matter. At some point, the energy balance changes. What was too expensive at lower density becomes useful at higher density. A particle that normally exists only briefly can become part of the preferred population. And once strange quarks are present alongside up and down quarks in large numbers, the question is no longer simply whether protons and neutrons have dissolved. The question becomes whether the new mixture they leave behind could be more stable than the matter from which it came. That is where the strange quark earns far more attention than its name alone would suggest, because this heavier member of the quark family may provide dense matter with exactly the additional freedom it needs to reorganize itself into something that ordinary nuclei could never become. Once protons and neutrons begin to lose their importance as separate objects, the dense material inside a neutron star faces a problem that ordinary matter almost never has to consider. It has an enormous number of quarks packed into a very small region, and most of those quarks begin as the two familiar varieties, up and down. At first, this seems perfectly reasonable. Up and down quarks are what protons and neutrons are made from, so if those particles gradually give way to a collective quark state, one might expect the result to be little more than their ingredients poured into a common container. But quantum matter does not simply preserve the proportions it happened to inherit. Once the quarks are able to participate in a larger shared state, the system can search for a more favourable arrangement, and at sufficiently high density a third option begins to matter. The strange quark, normally too heavy and too short-lived to become a permanent ingredient of ordinary nuclei, may suddenly find that the conditions have changed in its favour. The strange quark is one of 6 known quark flavours. Up and down are the lightest and dominate the stable matter around us. Strange is heavier than both of them, although far lighter than the heavier charm, bottom and top quarks. That position in the quark family is important. It is heavy enough that ordinary matter has no reason to maintain large populations of strange quarks, but not necessarily so heavy that extremely dense matter can always ignore it. The heavier quarks farther up the family remain far too costly for the conditions usually considered inside neutron stars. Strange sits in a more interesting middle ground. It is expensive, but perhaps not prohibitively expensive once the up and down quark populations have been compressed into sufficiently energetic states. Under ordinary circumstances, strange quarks appear inside unstable particles. A particle containing a strange quark can be produced in energetic collisions, remain around briefly, and then decay through the weak interaction into lighter particles. This is why you do not find strange atoms on the periodic table. There is no strange version of iron sitting quietly beneath the ordinary one waiting for someone to discover it. Stable nuclei are built from protons and neutrons, and those are dominated by up and down quarks. The strange quark belongs to a part of particle physics that usually reveals itself only when enough energy is available to create unusual particles, and those particles generally do not remain unusual for long. Deep inside compressed matter, however, the question changes. Instead of asking whether one isolated strange particle is stable, we ask whether a huge population of interacting particles can lower its total energy by allowing strange quarks to become part of the mixture. That is a very different calculation. A particle that is inconvenient on its own can become useful as part of a crowd because quantum mechanics forces large populations of identical particles to distribute themselves across available states. The more densely the particles are packed, the more expensive it becomes to keep forcing additional members of the same type into increasingly energetic states. Imagine a hotel with 2 enormous staircases, one for up quarks and one for down quarks. Every available room on the lower floors is occupied, so new arrivals are being sent higher and higher. The elevator is broken because this is clearly not a well-managed hotel, and the energy required to keep climbing is becoming uncomfortable. Somewhere nearby is a 3rd staircase. Entering it requires paying an additional fee because strange quarks are heavier. When the first 2 staircases are mostly empty, nobody bothers. The fee is not worth it. But as the occupied floors rise higher and higher, there comes a point when paying to enter the 3rd staircase can be cheaper than continuing to climb the first 2. Dense quark matter faces a quantum version of that choice. The comparison is simplified, but the basic reason is important. Up quarks have their own available quantum states. Down quarks have theirs. Strange quarks provide another collection of states. If only up and down quarks are present at enormous density, the highest occupied states can carry a substantial amount of energy. Allowing some of the population to become strange quarks can spread the quarks across 3 flavours rather than 2. The strange quark brings the penalty of additional mass, but the redistribution can reduce the energy associated with crowding the other flavors. If the density becomes high enough, those two effects can compete closely. Nothing in this process requires a strange quark to volunteer. Particle flavor can change through the weak interaction. The strong interaction binds and scatters quarks but preserves their flavor. The weak interaction has different rules and can transform one quark flavor into another when the overall process is allowed. Inside dense matter, weak reactions can therefore gradually adjust the populations of up, down, and strange quarks. The system does not have to preserve the exact mixture created at the moment deconfinement occurred. Given enough time, reactions can move it toward what physicists call weak equilibrium, meaning that the possible flavor-changing processes no longer gain anything by pushing the composition strongly in one direction. This adjustment is important because a neutron star is not a particle collision that disappears almost immediately. The material in an old neutron star can remain under enormous pressure for an extraordinarily long time. If a dense quark phase forms and weak reactions favour the production of strange quarks, the matter has time to change its composition. A state that begins mainly with up and down quarks does not necessarily remain that way. Strange quarks can appear until the different populations reach an equilibrium appropriate to the pressure and density. Electrical charge also influences the result. An up quark carries a positive electric charge equal to 2/3 of the magnitude carried by an electron. Down and strange quarks each carry a negative electric charge equal to 1/3 of that magnitude. The fractions sound peculiar, only because we are accustomed to treating the proton and electron as the natural units of electric charge. Combine two up quarks with one down quark and you obtain the positive charge of a proton. Combine one up quark with two down quarks and the charges cancel, producing a neutron. Quark matter is free to distribute these charges across much larger populations, but a macroscopic star cannot comfortably maintain an enormous net electric charge. The material therefore has to remain very close to electrically neutral. In quark matter containing only up and down quarks, achieving neutrality generally requires an imbalance between the two quark populations and often a population of electrons as well. This adds another constraint to an already crowded system. Strange quarks help because they carry the same negative electric charge as down quarks while opening an entirely new flavor of quantum states. In an idealized three-flavor mixture with similar numbers of up, down, and strange quarks, the positive charge of the up quarks can be balanced naturally by the negative charges of the other two flavors. Depending on the precise phase, electrons may become less important, and in certain highly symmetric paired states, the quark matter can be electrically neutral without needing a large electron population at all. The strange quark therefore provides more than an extra place to put particles. It also helps the matter solve its electrical bookkeeping. This is one of those situations where nature manages to make a concept sound both exotic and faintly administrative. The material is being crushed beyond nuclear density. Quarks may be escaping the identities of protons and neutrons, and the universe is still concerned about balancing the accounts. There is another subtlety hiding behind the word mass. Saying that the strange quark is heavier than the up and down quarks is true, but quark masses inside dense, strongly interacting matter are not always as simple as imagining three tiny balls placed on a kitchen scale. The apparent behavior of quarks depends on their interactions with the surrounding quantum fields and with one another. At lower densities, the effects associated with the strong interaction can make the energetic distinction between flavors behave differently from the simple masses quoted for nearly free quarks at very high energies. As density changes, the effective cost of including strange quarks can change too. This is one reason different theoretical models do not all predict exactly the same density at which strange quarks become important. The broader idea survives those details. At low density, strange quarks are too costly to become a permanent component of ordinary matter. At sufficiently high density, filling only the up and down quark states becomes costly as well. Somewhere between those limits, depending on the actual behavior of the strong interaction, the balance may shift. The heavier particle can become useful because the alternative has become even more expensive. This is not unique to strange quarks. Dense matter often produces particles that are absent from ordinary material because increasing density changes the energy balance. Muons can appear in neutron star matter, even though a block of iron does not need a stable population of muons. Hyperons, which are heavier relatives of protons and neutrons containing strange quarks, may become possible in some descriptions of neutron star cores. Other exotic arrangements have also been proposed. The general lesson is that the contents of matter are not fixed solely by asking which particles are lightest in empty space. Under extreme conditions, pressure, quantum statistics, interactions, and conservation laws determine which combination is preferred. Strangeness can therefore enter a neutron star before complete strange quark matter appears. If hyperons form, strange quarks are present but remain confined inside individual composite particles. This is different from a deconfined phase in which strange quarks participate directly in a shared quark medium. The distinction matters because a neutron star containing some strange particles is not automatically a strange star. The words are annoyingly similar, but the physics is not. A few strange ingredients inside otherwise hadronic matter are one possibility. A bulk state of up, down, and strange quarks is another. Suppose the density does rise far enough for deconfined quark matter to favour all three lightest flavours. The result would not necessarily look like a simple soup of independent quarks moving randomly in every direction. Quarks remain strongly interacting under the conditions likely to occur inside compact stars, and at low temperature they may form coordinated quantum states. One especially important possibility involves quarks pairing with one another. Fermions often discover surprisingly elaborate ways to organize themselves when they are cold and densely packed, and quarks are no exception. At extremely high density, theory predicts a particularly symmetric form known as the color-flavor-locked state. The full explanation involves properties of color charge and quark flavor that we do not need to express mathematically. The useful picture is that up, down, and strange quarks participate in a linked pattern of pairing. Color and flavor become tied together in the organization of the state, which is where the name comes from. The strange quark is essential to this three-flavor pattern. Instead of being a reluctant, heavy guest tolerated by the other particles, it becomes part of the structure that defines the phase. Whether real neutron star cores reach the conditions needed for this exact state is uncertain. The strange quark mass disrupts the perfect symmetry one would have if all three flavors behaved identically, and neutron star densities may lie in a complicated intermediate regime where several alternative forms of pairing compete. There may be partially paired phases, unpaired quark matter, mixed phases, or arrangements we have not yet pinned down confidently. The color-flavor-locked state is nevertheless valuable because it demonstrates something important. Once strange quarks become sufficiently abundant, they do not merely add another ingredient. They can change the collective organization of quark matter itself. This is one reason the interior of a neutron star can never be understood simply by listing which particles are present. Two materials could contain the same particle species, but organize them differently and therefore have different pressures, heat capacities, transport properties, and responses to magnetic fields. Water and ice contain the same molecules yet behave differently. Dense quark phases take that principle into a much less familiar realm, where the differences arise from patterns of quantum pairing and the strong interaction. The strange quark can also influence how the material carries energy. Different quark compositions provide different weak reaction pathways, which can affect neutrino production, and therefore the cooling of a compact star. Pairing can suppress some reactions and alter others. Transport of heat and momentum depends on which low-energy excitations are available in the material. None of this gives astronomers a simple sign reading strange quarks present, but it means the microscopic composition is not completely hidden. It can influence the long-term behaviour of the star, and that gives observers possible ways to test models indirectly. Rotation may offer another connection. A dense phase transition can change the distribution of matter inside a star and therefore its rotational properties. In a rapidly rotating compact star, changing internal composition as the star gradually loses rotational support can alter its structure. Researchers have considered whether transitions involving quark matter might leave subtle signatures in timing behaviour, although identifying such a signature uniquely would be difficult. Neutron stars contain enough complicated physics already that almost any unusual observation arrives with several suspects. The most dramatic laboratory comes when compact stars collide. During a neutron-star merger, matter is compressed, heated, and violently rearranged. Regions that did not contain quark matter before the collision may briefly cross conditions where new phases become favourable. Strange quarks could then become relevant in a rapidly changing environment, very different from the quiet interior of an old isolated star. The timescales are shorter and the temperatures higher, so weak interactions and phase conversion may not proceed exactly as they would in cold equilibrium matter. This complicates the physics, but it also creates another opportunity for quark matter to influence observable signals. Even if astronomers eventually found convincing evidence for deconfined quarks inside compact stars, however, identifying the strange component would remain a separate challenge. Up and down, quark matter can mimic some of the large-scale properties of three-flavor matter depending on the theoretical model. A transition in a gravitational wave signal might tell us that the interior changed phase, without politely identifying every quark involved. Determining whether strange quarks are abundant requires combining many pieces of evidence with a theoretical description reliable enough to connect those observations to microscopic composition. This is part of what makes strange matter both fascinating and frustrating. We're not dealing with an idea that can be settled by seeing one strange quark. Strange quarks have been observed for decades through the particles they help create. Their existence is not in doubt. The uncertainty concerns what billions upon billions of them might do collectively under conditions that are almost impossible to reproduce directly. The distinction is worth repeating because the name strange matter can make it sound as though the speculative part is the strange quark itself. It is not. The strange quark is a normal member of the standard collection of elementary particles, if normal is a word we are willing to use for an object that carries fractional electric charge and cannot be isolated. What remains hypothetical is the proposed macroscopic state in which strange quarks become a stable, abundant component of bulk quark matter. There is an interesting reversal here. In ordinary matter, strangeness is temporary. Create a strange particle, and the weak interaction eventually removes that strangeness through decay. In sufficiently dense quark matter, weak interactions may do the opposite. Instead of eliminating strange quarks until none remain, those same flavor-changing processes can help establish an equilibrium in which strange quarks are continually part of the preferred composition. The environment has changed what equilibrium means. Imagine returning to the hotel. Earlier, the strange staircase was expensive to enter, so anyone who wandered onto it soon found a way back downstairs. Now the first two staircases are packed to such high floors that the extra entry cost is no longer a disadvantage. People begin using all three, and after enough time the building settles into a new distribution. Nobody running the hotel has changed the rules. The crowd has changed the consequences of those rules. This is why density can create behaviour that looks surprising from the perspective of empty space. A particle mass tells us something important, but it does not by itself determine the composition of dense matter. The relevant question is the energy of the entire many-particle system. Each quark influences the available states, electrical balance, interactions, and possible pairing patterns of the others. Strange quarks are admitted not because nature has developed a preference for exotic names, but because the collective state may benefit from having them. As more strange quarks appear, the distinction between ordinary nuclear matter and the new phase becomes increasingly profound. Ordinary matter organizes quarks into protons and neutrons, then organizes those into nuclei, then surrounds the nuclei with electrons to form atoms. Three-flavor quark matter removes several layers of that architecture. There need be no separate atomic nuclei, and no ordinary collection of individual nucleons in the same sense. The quarks themselves form the bulk material, with their populations and interactions providing the pressure needed to support the matter. If you could somehow remove a tiny amount of such material from the star, another set of questions would immediately appear. Would it remain together once the enormous external pressure disappeared, or would it expand and convert back into ordinary hadrons? Would the strange quarks remain part of a stable mixture, or would the material decay until only ordinary nuclei were left? The answer depends on something we have carefully avoided assuming so far. Dense matter can favour strange quarks at enormous pressure without strange quark matter being stable at ordinary pressure. That distinction separates two versions of the story. In one, strange quark matter exists only because the centre of a neutron star squeezes it hard enough. Remove the pressure and ordinary nuclear matter wins again. In the other, far more remarkable possibility, a sufficiently large mixture of up, down and strange quarks remains energetically favoured even when no external pressure is forcing it into that state. In that case, strange matter would not simply be an exotic phase created by neutron star conditions. It could represent a deeper stable form of strongly interacting matter. The strange quark has therefore taken us to a much larger question than whether a third flavour appears in a crowded stellar core. We began with a heavier particle that ordinary matter quickly gets rid of. Compression gave it room to compete. Weak interactions gave the system a way to produce it. Electrical neutrality gave it another reason to be useful. Quantum statistics allowed the third flavour to relieve some of the crowding of the first two. Pairing may give it a role in entirely new collective phases. None of those points by itself tells us that strange matter is the preferred form of matter under all conditions, but together they make that possibility difficult to dismiss without doing the calculation. The next step is therefore not to ask whether strange quarks can exist in dense matter. They can, at least within well-established particle physics and plausible descriptions of sufficiently compressed matter. The harder question is what happens after they arrive. If the three-flavour mixture settles into a lower energy state than matter built from ordinary protons and neutrons, then strange matter stops being merely another exotic phase available inside a star. It becomes a candidate for something much more unsettling and much more interesting. A form of matter that may be more stable than the nuclear material from which planets, stars, and people are made. The possibility that strange quarks might become abundant inside extremely dense matter is already unusual, but it does not automatically make strange matter more stable than the material around us. A neutron star can force particles into arrangements that would never survive on their own. Enormous pressure can support phases of matter that disappear as soon as that pressure is removed, just as conditions deep inside a planet can produce structures that would not remain unchanged at the surface. The more remarkable version of the strange matter idea asks something different. Suppose a large enough mixture of up quarks, down quarks, and strange quarks did not need the crushing pressure of a neutron star to remain together. Suppose that after the matter had formed, it could remain bound even when the external pressure dropped away. Then strange quark matter would not merely be one exotic phase hidden in the centre of a compact star. It could be a candidate for a more deeply stable form of strongly interacting matter than the protons and neutrons from which ordinary nuclei are built. To understand what physicists mean by more stable, it helps to forget for a moment about whether something looks solid or survives for a long time. Stability in this context is mainly a question of energy. Nature tends to favour arrangements with lower total energy when a path between those arrangements is available. A collection of particles can therefore be compared with another collection containing the same overall amount of conserved material, and physicists can ask which arrangement has the lower energy. Ordinary atomic nuclei are remarkably stable by everyday standards. Iron and nearby nuclei are among the most tightly bound arrangements of protons and neutrons found in normal matter. They can sit inside planets for billions of years without showing any interest in becoming something more exotic. The strange matter hypothesis asks whether a sufficiently large piece of three-flavor quark matter could possess an even lower energy for the same amount of baryonic material. If it could, then ordinary nuclear matter would not be the lowest possible state available to the strong interaction. That phrase, lowest possible state, is sometimes called the ground state. It is the arrangement nature would prefer if all relevant transformations were allowed to occur and the system had a way to reach the lowest energy configuration. This does not mean that everything instantly arrives there. A ball sitting in a small hollow on the side of a hill can remain there even though a deeper valley exists farther below. To reach that valley, the ball first has to climb over the ridge separating the two. If it lacks enough energy to cross the ridge, it stays in the shallow hollow. From a practical point of view, it may remain there indefinitely. Matter can behave in a similar way. An arrangement may not be the absolute lowest energy state, and yet survive for an extremely long time because the transition to something lower is suppressed by barriers, conservation rules, or interactions that operate very slowly. This distinction is crucial because otherwise the strange matter hypothesis seems to create an immediate contradiction. If strange matter were more stable than ordinary nuclei, why are there any ordinary nuclei left? Why did the carbon in your body not convert long before you were born? Why has Earth survived for billions of years while stubbornly refusing to become a compact lump of quarks? The answer is that absolute stability and easy conversion are not the same thing. Even if strange quark matter lies lower in energy, ordinary matter begins in a completely different microscopic arrangement. Its quarks are confined inside protons and neutrons. Almost all of those quarks are up and down quarks. To become strange matter, many of them would need to enter a deconfined state, and a substantial fraction would need to change flavor through the weak interaction. The system may also need to create a sufficiently large seed of the new phase before conversion becomes favorable overall. Those requirements can create an enormous barrier between ordinary nuclei and hypothetical strange matter. There is another condition that any successful strange matter model has to respect. Matter made only from up and down quarks cannot simply be allowed to become more stable than ordinary nuclei under normal conditions, because if it were, the nuclei around us would have a much easier route into deconfined quark matter. The fact that ordinary nuclear matter survives places a powerful restriction on theoretical models. A viable version of the traditional strange matter hypothesis therefore needs a rather specific situation. Two-flavor quark matter should remain less favorable than normal nuclei, while three-flavor matter containing strange quarks may become favorable. The strange quark is not an optional decoration added after the interesting physics has happened. It is what can potentially move quark matter into a different energy range without making ordinary nuclei obviously unstable. This creates what physicists often describe as a stability window. The properties assumed for dense quark matter have to fall within a range where the three-flavor state is bound strongly enough to compete with nuclear matter, but the two-flavor state is not so strongly bound that the existence of ordinary nuclei becomes difficult to explain. The location and even existence of this window depend on how the strong interaction behaves at high density. That is one reason the question has remained open for so long. We know the underlying theory of quarks and gluons, but extracting reliable predictions for cold matter at the densities where strange matter might become relevant is extraordinarily difficult. Theoretical models therefore represent aspects of the strong interaction in different ways, and small changes in those assumptions can determine whether strange matter ends up slightly above or slightly below ordinary nuclear matter in energy. One of the simplest historical approaches treats quarks as though they occupy a region in which they can move relatively freely, while the surrounding vacuum resists their existence with an effective energy cost. You can picture this very loosely as placing quarks inside a bubble that has to be maintained against the properties of the vacuum outside. The quarks gain advantages from spreading through available quantum states, but creating and maintaining the region itself carries a cost. Change that cost and you change whether a large piece of quark matter is favourable. Make it too expensive and ordinary nuclear matter wins. Make it sufficiently inexpensive and three-flavour quark matter can become competitive. The real strong interaction is more complicated than this picture, but models of this kind were important in demonstrating that absolutely stable strange matter was not obviously forbidden by known physics. The strange quark mass then enters as another piece of the balance. If strange quarks were just as light as up and down quarks, distributing the particles across three flavours would offer a very clear advantage at high density. The populations could spread more evenly through the available states, reducing the amount of energy associated with crowding any one flavour. But strange quarks are heavier, so producing them carries a penalty. Whether the three-flavour mixture wins depends partly on whether the reduction in crowding and other interaction effects outweigh the extra mass. This is why the argument is not simply that three types are always better than two. Nature is comparing several contributions at once, and the result can change as density changes. The interactions among the quarks complicate the accounting further. Quarks are not an ideal collection of particles ignoring one another while politely occupying separate quantum states. They exchange gluons, they can form correlated pairs, and their effective behaviour changes with density. Attractive pairing between quarks can lower the energy of certain dense phases. Repulsive contributions can influence pressure and the ability of the material to support a compact star. The strange quark mass can disrupt otherwise symmetrical arrangements among the three flavours. Every one of these effects can alter the answer to what sounds like a very simple question. Is strange matter lower in energy than nuclear matter? By the time the strong interaction has finished adding conditions to the question, Simple has quietly left the room. Suppose, though, that nature chooses parameters that do make bulk strange quark matter absolutely stable. One immediate consequence would be that this material could be self-bound. A neutron star made from ordinary neutron-rich matter is held together primarily by gravity. Remove enough gravity, and the material does not remain as a star-sized lump. Strange quark matter, if absolutely stable, could in principle be held together by the strong interaction itself. Gravity would still matter enormously for a massive strange star, but it would not be the only reason the material stayed assembled. Even near the surface, the quark matter could remain bound until it reached a relatively sharp boundary, rather than gradually thinning in exactly the same way as ordinary stellar matter. This would make a strange star structurally different from an ordinary neutron star even if both objects had similar masses and similar overall sizes. A neutron star owes its existence to a competition between gravity and the pressure of dense matter. A hypothetical strange star could contain matter that is already bound in bulk before gravity is included. Gravity would compress it further and shape the star, but the underlying material would have its own binding. That difference can affect how the mass and size of low-mass objects relate to one another, what happens near the stellar surface, how oscillations behave, and what kinds of crust the object might support. Unfortunately for astronomers, the differences are not guaranteed to produce one simple, unmistakable observation. Nature has once again declined to provide a label on the outside. Absolute stability would also change the way we think about neutron star interiors. If a sufficiently large seed of strange matter formed inside a neutron star and the strange phase were genuinely lower in energy than nuclear matter, the surrounding material could in principle convert into the new phase. The conversion would involve deconfining the quarks and using weak interactions to produce the equilibrium strange component. This would not necessarily happen everywhere at once. A conversion front could propagate through the dense stellar material as one phase replaced another. The final object might be mostly or entirely composed of strange quark matter, perhaps with a thin layer of ordinary material remaining near the surface under certain conditions. This possibility sounds dramatic because it is dramatic, but there is an important restraint on how we talk about it. We do not know that such conversions happen in nature. We do not know that absolutely stable, strange matter exists. Models can explore how a neutron star might transform if the hypothesis is correct, but a theoretical conversion scenario is not evidence that an observed star has undergone one. Compact objects can produce violent bursts, changes in rotation, gravitational waves, neutrinos, and other signals for many reasons. Connecting any particular event uniquely to strange matter requires far more than discovering that a model can produce something exciting. The same caution applies to the famous idea that strange matter could convert ordinary material merely by touching it. That version tends to lose several pieces of physics, while travelling from research papers into popular imagination. Ordinary atoms at low pressure are not the same as neutron star matter already compressed near or beyond nuclear density. Even if a piece of stable strange matter existed, a normal nucleus approaching its surface would encounter electric and quantum effects, and converting its up and down quarks into an equilibrated strange mixture would require weak interactions. The behaviour of the interface depends on the charge of the strange matter, the size of the object, its surface structure, and the surrounding conditions. It is therefore misleading to picture strange matter as a contagious substance operating like fire through dry paper. The survival of Earth provides a useful reality check on catastrophic claims. Cosmic rays have been producing energetic particle collisions in natural environments for the entire history of the planet and long before it existed. Much more energetic events occur throughout the universe. If ordinary high-energy collisions readily produced dangerous stable objects that then converted everything they encountered, nature would have had an enormous amount of time and many opportunities to demonstrate the effect. Searchers for strange matter have nevertheless found no confirmed stable strange objects. None of this proves that every conceivable form of strange matter is impossible, but it tells us that the simple nightmare scenario is not a sensible description of what the evidence currently supports. There is another complication that becomes important when we stop imagining an infinite piece of strange matter and consider something finite. Bulk matter can behave differently from a tiny droplet because the particles near a surface do not experience the same environment as particles deep inside. A large piece contains so much interior material that surface effects contribute only a relatively small fraction of its total energy. Make the object smaller and the surface becomes increasingly important. The strange quark is heavier, and its behaviour near the boundary may differ from that of the lighter flavours. Electric charge can develop. Curvature of the surface matters. Quantum shell effects may influence which small configurations are favoured. As a result, a model can allow absolutely stable bulk strange matter, while predicting that very small lumps are unstable. This point will matter when we eventually turn to strangelets, because a strangelet is essentially the finite version of the bulk idea. It is tempting to imagine cutting a tiny piece from stable, strange matter, and assuming the fragment automatically inherits all the properties of the infinite material. That is not necessarily true. A lake can support waves that make little sense in a droplet, and a large crystal can have properties that change when only a few atoms remain. Strange quark matter has its own size-dependent effects. The question of whether bulk matter is stable therefore comes first. Only after that can we ask how small a stable piece might be. There is also a useful distinction between absolute stability and metastability. Suppose strange quark matter exists, but its energy is slightly higher than that of ordinary nuclear matter when external pressure vanishes. It could still survive for a considerable time if converting back into hadrons requires crossing an energy barrier. In that case, the material would be metastable rather than absolutely stable. It might exist inside compact stars because high pressure favours it, and it might even persist under some circumstances after conditions change, but it would not be the true lowest energy form of baryonic matter. This middle possibility is easy to overlook because the popular version of the subject tends to offer only two choices. Either strange matter does not exist, or it is the ultimate form of matter. Physics is rarely so considerate. Another possibility is that quark matter can be absolutely stable, while containing fewer strange quarks than the traditional hypothesis expects. Modern studies have explored scenarios in which strongly interacting quark matter may be self-bound without requiring the old picture of nearly equal up, down, and strange populations. That does not invalidate the strange matter hypothesis, but it shows how much uncertainty remains in the dense regime. The broad question is really about what arrangement of quarks minimizes the energy of strongly interacting matter. Strange matter is one particularly elegant candidate, not a result already selected by nature. Why then did the idea become so influential? Partly because it connects a microscopic property of quarks to enormous astrophysical consequences. A relatively small difference in energy per unit of matter could decide whether neutron stars contain quark cores, whether some compact objects are strange stars, whether stable quark nuggets could survive from violent astrophysical events, and perhaps whether relics of quark matter could have persisted from the early universe. The hypothesis makes predictions across particle physics, nuclear physics, astrophysics, and cosmology. Few ideas manage to involve the smallest known constituents of ordinary matter and entire stars without changing subjects. There is also something conceptually unsettling about the possibility. We naturally assume that ordinary matter deserves its name because it represents the normal endpoint of physical organization. Protons and neutrons feel fundamental in everyday thinking, even after we learn that they contain quarks. Atomic nuclei seem like the stable foundation on which everything else is constructed. The strange matter hypothesis turns that perspective around. Perhaps nuclei are not the deepest stable arrangement of quarks. Perhaps they are merely the arrangement selected by the low-pressure environment in which most visible matter happens to live. Under that interpretation, the atoms around us are not false or fragile. They are simply local winners. A useful comparison is carbon. Under one set of conditions, one arrangement is favoured. Under another, a different structure becomes possible. The atoms do not need to change identity for the material properties to change dramatically. Strange matter would take this principle much deeper, because the reorganization happens inside what we normally call nuclear particles. Instead of rearranging atoms into a new crystal, the system rearranges the quarks from which the nuclei themselves are built. The scale is smaller, the conditions are far more extreme, and the consequences could extend across an entire star. There is an even more important difference. Ordinary phase changes usually leave us with the same conserved particles arranged differently. Strange matter requires weak interactions to change the flavor composition. A large population that begins with up and down quarks must generate strange quarks as it approaches equilibrium. That takes time, however short by human standards it might become in dense stellar material. The strong interaction can reorganize quarks extremely rapidly, but it does not change one flavor into another. The weak interaction handles that part of the conversion. The formation of stable strange matter would therefore involve different fundamental interactions performing different jobs, with gravity potentially providing the compression that makes the process favourable in the first place. If such a transformation started in the core of a compact star, the energy released would depend on the difference between the original and final states, and on the detailed conversion process. Even a modest energy advantage per particle becomes enormous when multiplied across a stellar quantity of matter. This has encouraged proposals connecting phase conversion with powerful astrophysical transients. Yet the same warning applies as before. A large theoretical energy reservoir is not enough to identify a real astronomical event. The energy must emerge in a particular way, on a particular timescale, and produce signals distinguishable from more conventional stellar processes. Astrophysics has no shortage of mechanisms capable of making loud noises. observations can nevertheless squeeze the theory from several directions. We know very massive compact stars exist, which means any proposed strange matter description must be capable of producing enough pressure to support them. Measurements of stellar radii and tidal deformability restrict how compressible the material can be. Merger observations test the behavior of dense matter under violent conditions. Searches for unusual particles constrain the abundance of stable fragments. Nuclear physics restricts which models remain compatible with the properties of ordinary matter. The strange matter hypothesis has to survive all of these tests simultaneously. It cannot succeed by explaining one observation beautifully while quietly breaking everything else. So far, nature has not given us a decisive answer. Stable strange quark matter has not been confirmed. Neither has the possibility been eliminated on completely general theoretical grounds. The answer depends on the properties of the strong interaction in a regime where our calculations remain uncertain. That makes the hypothesis less satisfying than a simple yes or no, but much more representative of how research actually works. There are areas of physics where the equations are known, the ingredients are known, and yet extracting the behavior of a large complicated system remains extraordinarily difficult. The most important point is therefore not that strange matter is definitely more stable than ordinary matter. It is that known physics leaves open a serious possibility that a three-flavor quark state could occupy an energy range below ordinary nuclear matter under the right conditions. If that possibility is realized, the material would be self-bound and capable of existing without the enormous external pressure normally associated with quark matter. Ordinary nuclei could still remain effectively stable, because reaching the strange state would require a difficult sequence of deconfinement, flavor change, and formation of a sufficiently favorable region of the new phase. There is no contradiction in having matter that survives for billions of years, while another lower energy arrangement remains almost impossible to reach. That leaves us with a practical problem. Bulk strange matter is an enormous theoretical object. In calculations, it can be treated as though the material extends far enough that the surface hardly matters. Nature does not have to provide us with an infinite sample. If strange matter is created in a star, a collision, or some event in the early universe, pieces of it may be finite. Some could be star-sized, others could be much smaller. Once the size shrinks, the surface begins to matter, the electric charge becomes important, and the neat conclusions drawn for an enormous volume can change. A tiny piece of strange matter would therefore be more than a miniature copy of a strange star. It would have its own balance of quark flavors, its own surface energy, its own charge, and perhaps a minimum size below which the strange arrangement could no longer survive. If such objects exist, they might travel through space, appear in cosmic rays, become trapped in ancient material, or pass through detectors built specifically to look for something with properties unlike any ordinary nucleus. Physicists have given these hypothetical droplets a suitably compact name. They are called strangelets, and asking whether even one could remain stable takes the question of strange matter out of the inaccessible interior of a star and places it, at least in principle, within reach of an experiment. If strange quark matter really can be more stable than ordinary nuclear matter, then the next question is an obvious one. Does it have to come in quantities large enough to build an entire star, or could nature make a much smaller piece? A fragment containing far fewer quarks than a strange star is usually called a strangelet. The name is wonderfully modest for an object that, if it exists, could represent a completely different way of arranging the ingredients of nuclear matter. Instead of protons and neutrons bound together inside a nucleus, a strangelet would contain up quarks, down quarks, and strange quarks participating in one compact piece of quark matter. You can think of it as a tiny droplet taken from the hypothetical strange matter we have been discussing, although that comparison immediately creates a problem. A droplet is not always just a smaller version of an ocean. Once an object becomes small enough, its surface starts influencing almost everything about it, and strange matter is no exception. The distinction between bulk strange matter and a strangelet is important, because many of the arguments that make an enormous amount of strange matter potentially stable become less reliable as the amount shrinks. Imagine a very large block of material. Most of the particles are buried deep inside it, surrounded on every side by other particles. Only a small fraction sit near the surface. If you make the block smaller, the proportion of particles near the surface increases. Keep shrinking it, and eventually almost everything is close enough to the boundary that surface effects matter. A strange star could contain an almost unimaginable number of quarks, so the details of its outer boundary contribute very little to the average energy of the material deep inside. A strangelet might contain so few particles that the boundary can decide whether the entire object survives. This produces what physicists call surface energy. Particles inside a large piece of matter can interact with neighbours in every direction, while particles near an edge experience a different environment. Creating the surface therefore usually costs energy. For strange quark matter, the effect can be particularly important, because strange quarks are heavier than up and down quarks and may respond differently near the boundary. A small strangelet may contain fewer strange quarks near its surface than the simple bulk picture would suggest. That changes the composition, the total energy, and even the electrical charge. The smaller the strangelet becomes, the harder it is to pretend that it is simply a tiny scoop of perfectly uniform bulk matter. Curvature adds another contribution. A large flat surface and a tiny curved surface are not equivalent. If the strangelet is small enough, the curvature of its boundary can influence the energy almost as strongly as the surface itself. These corrections may sound like annoyingly technical details added by physicists after everyone thought the problem was finished, but they can determine whether a hypothetical strangelet is stable. Bulk strange matter could, in principle, be energetically favoured, while very small strangelets are not. There might be a minimum size below which the surface and curvature costs become too large, and the quark droplet breaks apart into ordinary particles. That gives strangelets a very different personality from ordinary atomic nuclei. An atomic nucleus is also a tiny collection of strongly interacting particles, but its basic ingredients are protons and neutrons. A strangelet would replace that familiar nuclear architecture with one region of deconfined quark matter. Depending on the model, its size could range from something comparable to a nucleus all the way toward much larger macroscopic objects. There is no single agreed strangelet size because strangelet is a category rather than one specific particle. Asking how large a strangelet is can be a little like asking how large a rock is. There are some practical boundaries on the word, but you are still going to need more information. The number of quarks also introduces an effect that disappears when we imagine an infinitely large piece of matter. Quantum states come in discrete arrangements. In bulk matter, there are so many particles that those individual levels blend into an almost continuous pattern, making average descriptions extremely useful. In a small strangelet, however, the exact way the available states fill can matter. Certain particle numbers may produce especially favourable arrangements, while neighbouring numbers may be less stable. This is similar in spirit to shell effects in atomic nuclei, where particular numbers of protons and neutrons lead to unusually stable configurations. Strangelets can have their own shell structure because the quarks have to occupy allowed quantum states inside a finite region, so even if someone gave us the exact properties of bulk strange matter, we could not immediately predict every possible strangelet by cutting the bulk result into smaller pieces. Size matters, surface structure matters, curvature matters, quantum state filling matters, the strange quark mass matters, the way quarks interact matters, pairing between quarks may matter, electrical charge matters. At this point, the hypothetical simple droplet has developed a fairly demanding list of requirements for something that has not yet been confirmed to exist. Electrical charge gives strangelets one of their most distinctive possible features. Ordinary nuclei contain positively charged protons and neutral neutrons, so the electric charge tends to increase substantially as the nucleus contains more protons. Strange quark matter distributes charge differently. Up quarks carry positive charge, while down and strange quarks carry negative charge. In large 3-flavor quark matter, those populations can come close to balancing one another. A strangelet may therefore carry a relatively small positive charge compared with an ordinary nucleus of similar mass. The exact charge depends strongly on the strangelet model and size. Small strangelets may have proportionally fewer strange quarks near the surface, leaving a positive excess. Larger strangelets can approach a different balance. If the quarks form certain paired phases, the relationship changes again. What remains useful experimentally is the broad possibility that a strangelet could be much heavier than an ordinary nucleus carrying the same electric charge. That gives physicists something unusual to look for. A detector might encounter an object behaving like an exceptionally massive nucleus without having the charge expected from any ordinary isotope. A strangelet small enough to resemble a giant atomic nucleus would not necessarily carry its own ordinary electrons inside it. Electrons are much lighter and occupy much larger characteristic regions than the quarks. For sufficiently small strangelets, electrons would be more naturally found outside rather than embedded throughout the quark droplet. As strange matter becomes larger, electrons can participate differently in maintaining overall neutrality, depending on the phase of the quark matter. Once again, the behavior changes with scale, and there is no single picture that describes everything from a tiny strangelet to a strange star. All of this assumes that a strangelet has somehow formed in the first place. That is not a trivial step. If strange quark matter is stable, nature still needs a process capable of assembling enough quarks in the appropriate state. One proposed source is the violent interaction of compact stars. If strange stars exist and two of them collide, material could potentially be torn away and ejected into space. The original chunks might be enormous by particle standards and then fragment into smaller pieces as they travel through the surrounding environment. Some of those fragments could become strangelets capable of surviving long journeys through the galaxy. A collision involving a strange star and another compact object could provide similar opportunities for ejecting quark matter, although exactly how much survives would depend on the dynamics of the event and the properties of the material. Remember that strange matter must be self-bound for an isolated fragment to remain intact once it leaves the star. If strange quark matter is stable only because stellar pressure maintains it, ejecting a piece into lower pressure surroundings would not produce a long-lived strangelet. The fragment would tend to convert into ordinary hadrons instead. The existence of cosmic strangelets therefore depends on the stronger version of the strange matter hypothesis. The early universe has also been considered as a possible source. Very shortly after the beginning of cosmic expansion, the universe was hot and dense enough for quarks and gluons to exist in conditions radically different from those today. As the universe expanded and cooled, quarks became confined into the hadrons that later formed atomic nuclei. If the transition occurred in a way that trapped regions of quark matter, some researchers have considered whether quark nuggets might have survived. Under suitable assumptions, those relics could contain strange quarks and persist for very long periods. The details are highly model dependent, and there is no confirmed population of primordial strange nuggets waiting in a museum cabinet. But the idea illustrates how strange matter could arise without needing a modern neutron star to manufacture it. Whatever the source, surviving strangelets travelling through the galaxy would behave somewhat like extremely unusual cosmic rays. Charged particles moving through the galaxy are influenced by magnetic fields. Ordinary cosmic rays, which include atomic nuclei, can be accelerated by energetic astrophysical environments and wander through interstellar space before some of them reach Earth. A charged strangelet could participate in a similar journey. Because its mass compared with its electric charge could be very different from that of an ordinary nucleus, its response to magnetic fields and its behavior in a detector could also be distinctive. The journey would not necessarily be peaceful. Interstellar space is sparse by earthly standards, but it is not completely empty. A strangelet travelling enormous distances can collide with atoms and other particles. High-energy collisions may break pieces from it or change its composition. Lower-energy interactions may slow it down. The details depend on its size, charge, speed, and internal binding. Some calculations suggest that if absolutely stable strangelets are produced astrophysically, a fraction could survive galactic propagation and reach environments where experiments might detect them. The uncertainty is large because it begins with an object we have never confirmed, produced by sources whose strange matter content we do not know, then asks how many survive a journey through a galaxy whose magnetic fields are complicated. There are easier ways to plan a delivery. The strangelet could also change as it travels. A sufficiently energetic collision might remove particles from the droplet. If it becomes too small, surface effects could push it below the minimum stable size, and it might decay into ordinary hadrons. Larger fragments would generally have a better chance of surviving, although their acceleration and abundance would differ. This means a strangelet population arriving near Earth would not necessarily resemble the population originally ejected from its source. Galactic travel could act as a filter, favouring particular sizes and energies. One environment has been especially useful when physicists think about searching for strangelets that have arrived from space. The Moon has no thick atmosphere like Earth's to interfere with incoming cosmic particles, and its surface has remained comparatively undisturbed for enormous periods. Material arriving from space can become embedded in lunar soil and remain there without the active geology and weather that constantly recycle much of Earth's surface. Samples returned from the Moon therefore provide something like an ancient collection plate that has been exposed to cosmic radiation for a very long time. Scientists have taken advantage of this by searching lunar material for objects with the unusual combinations of mass and charge expected for stable strange matter. No convincing strangelet was found in those searches, allowing experiments instead to place upper limits on how abundant certain kinds of strangelets could be. A non-detection might sound disappointing, but it is exactly how hypothetical ideas are narrowed. If a model predicts that strange stars should fill the galaxy with easily detectable strangelets, and increasingly sensitive experiments find none, that version of the model becomes harder to maintain. Particle accelerators provide another possible environment for creating small quark systems, which has occasionally led to rather dramatic misunderstandings. Heavy ion colliders smash large nuclei together at enormous energies and produce matter in conditions where quarks and gluons can become deconfined. It is reasonable to ask whether such collisions might also produce strangelets. Searches for unusual strange objects have therefore accompanied high-energy nuclear physics for decades. What does not follow is the claim that colliders are likely to manufacture dangerous strangelets capable of consuming the planet. There are several reasons for that. The first is that the matter created in collider experiments is extremely hot, while stable strange matter, if it exists, is generally associated with cold, dense conditions. High temperature tends to work against assembling a well-bound cold strangelet. The second is observational. Natural cosmic rays have been producing collisions at energies comparable with or beyond human-made accelerators for billions of years. They strike planets, stars, and other astronomical objects without evidence of strange matter catastrophes. Dedicated safety analyses have used these natural collisions, together with what experiments tell us about particle production, to conclude that strangelets produced by heavy ion colliders do not pose a danger. The imagined catastrophe usually assumes a strangelet with negative electric charge that is stable, produced easily, slow enough to remain nearby, and capable of absorbing ordinary nuclei while growing. Every one of those assumptions has problems. Many theoretical strangelet models favour positive charge for the relevant small objects. Stable production in hot collisions is already considered highly unfavourable. Natural high-energy collisions provide an enormous record of similar processes occurring without destroying astronomical bodies. The frightening story survives largely because a phrase like strange matter converts everything it touches is much easier to remember than several paragraphs about surface charge, production rates, collision kinematics, and astrophysical constraints. A stable strangelet, if one exists, would still interact with ordinary matter. It carries strong interacting quarks after all. But interaction is not the same as automatic conversion. When an ordinary nucleus approaches, electric forces can influence whether the two objects even make close contact. If they do collide, the outcome depends on energy, strangelet size, and internal structure. The nucleus might fragment, quarks might rearrange, some material might be absorbed under the right conditions, other interactions could damage the strangelet instead. There is no general rule that every encounter causes immediate growth. Inside a neutron star, the circumstances could be very different. Matter there is already extraordinarily dense, and nuclei in the deep interior have long since ceased behaving like normal atoms. If an absolutely stable strangelet were placed in sufficiently dense nuclear matter, conversion could be much more favourable because the surrounding material is much closer to the conditions needed for deconfinement. This is one reason hypothetical strangelets have been discussed in connection with compact stars. A seed entering a neutron star might, under some models, trigger conversion of dense stellar matter into strange quark matter. That possibility leads to an interesting astrophysical argument. If stable strangelets are common in the galaxy and can efficiently convert neutron stars, then old neutron stars should have had many opportunities to encounter them. Depending on how readily the conversion works, the survival of a large population of ordinary neutron stars could therefore constrain how common strangelets are. The difficulty is that we do not always know whether a compact star is an ordinary neutron star or a strange star merely by looking at it. If strange stars mimic many neutron star properties, the argument becomes less straightforward. Once again, the universe manages to turn what sounds like a clean test into a discussion involving several uncertain assumptions. Strangelets could span much larger masses than the tiny nuclear scale objects most people imagine. As the amount of strange matter grows, its description gradually moves away from particle physics and toward astrophysics. Somewhere along that enormous range, the object becomes a strange quark nugget, rather than something we would casually call a strangelet, although terminology varies. Continue adding matter and gravity becomes increasingly important. Add enough, and eventually you are discussing a strange star. There is no fundamental wall separating these categories. They represent different size regimes of the same broad hypothetical material, with different physical effects becoming dominant along the way. At the small end, quantum shell effects and surfaces dominate. At intermediate sizes, the material begins behaving more like bulk strange matter, while electrical effects remain important. At very large sizes, gravity has to be included. A single hypothesis therefore connects objects smaller than atoms with objects containing more mass than the Sun. Few materials can claim quite that range on their imaginary product brochure. This range of possible sizes also explains why strangelet searches take different forms. An experiment designed to detect a nuclear-scale strangelet does not necessarily work for a macroscopic nugget. A small charged strangelet might pass through a magnetic spectrometer like an anomalously massive cosmic ray nucleus. A much larger compact nugget could interact with matter in a completely different way. Lunar samples test another part of the possibilities. Heavy ion experiments test production in collisions. Astrophysical observations can constrain the existence of large populations indirectly. No single search covers the entire strange matter landscape. There have occasionally been unusual events in cosmic ray experiments that inspired speculation about strangelos, particularly events with unexpectedly high mass, unusual charge, or strange penetration behaviour. None has become a universally accepted detection. This distinction matters because new particles are rarely established from one curious event. Detectors have backgrounds, Measurements have uncertainties. Ordinary physics can produce surprising signatures. A convincing Strangelets discovery would need an event whose properties fit the strange matter. Interpretation, resist conventional explanations, and ideally appear repeatedly or be confirmed independently. The properties researchers would want to measure sound simple in principle. How massive is the object? How much electric charge does it carry? How fast is it moving? How does it lose energy while passing through material? Does it interact like an ordinary nucleus? Does its mass and charge combination correspond to any known isotope? A strangelet might stand out because those answers do not fit the ordinary nuclear chart. In practice, measuring all of them accurately for a rare particle arriving from space is considerably harder than writing the questions down. This is where strangelets become scientifically valuable even without a discovery. They turn the abstract strange matter hypothesis into something experiments can attempt to falsify directly. A strange star may hide its composition beneath a surface thousands of meters above its deepest quark matter. A strangelet, by contrast, would be the material itself arriving at the detector. There would be no need to infer its existence from a star's radius or cooling history if a stable fragment could be captured and studied. Finding one would have consequences far beyond adding another entry to the particle catalogue. A confirmed stable strangelet would demonstrate that quark matter can remain bound in a finite object outside the crushing pressure of a compact star. Depending on its properties, that could provide strong evidence that bulk strange quark matter is stable as well. It would tell us something profound about the behaviour of the strong interaction at high density and force us to reconsider what the lowest energy form of baryonic matter actually is. Not finding them is informative too, although less decisive. Perhaps strange matter is not absolutely stable. Perhaps stable strangelets exist only above a size our current searches do not cover. Perhaps they are produced so rarely that none has reached our detectors. Perhaps strange stars exist but do not eject much material. Perhaps strangelets are destroyed while travelling through the galaxy. Perhaps their charge and interaction properties differ from the assumptions used to design a particular experiment. A null result closes pieces of the map without necessarily burning the whole map. That is why the search has continued in so many different places. Researchers can look in cosmic rays, ancient material, accelerator collisions, and astronomical systems. Each approach asks a slightly different question about the same hypothetical droplets. Strangelets are useful because their existence would connect phenomena separated by absurd differences in scale. The internal behaviour of quarks could determine what passes through a detector near Earth, what remains buried in lunar soil, what emerges from a compact star collision, and what some of the densest stars in the universe are actually made from. For now, the tiny droplets remain hypothetical. We can calculate possible masses, charges, surface structures, and survival conditions. We can imagine how they would move through magnetic fields and how they might form when compact objects collide. We can search materials that have been exposed to cosmic particles for billions of years. What we do not yet have is a strangelet that everyone can point to and say that the strange matter question has finally become an experimental fact. The absence of that decisive object brings us to the larger problem facing the entire subject. Strange matter may hide in stellar cores where we cannot reach it, appear in fragments so rare that none has crossed the right detector, or leave indirect effects that can be confused with more ordinary physics. If nature has made strange matter somewhere, finding it will require us to recognize consequences rather than simply waiting for a piece to land conveniently on a laboratory bench. That means asking what strange matter would do to stars, collisions, cosmic rays, and matter itself, then searching for observations that ordinary nuclear physics struggles to imitate. Recognizing strange matter would be much easier if nature provided a sample with a label attached to it, but most realistic possibilities are considerably less convenient. If strange matter exists, much of it may be buried beneath the surface of compact stars, hidden under layers of material that no telescope can see through directly. Smaller strangelets may be extraordinarily rare, electrically unusual, or difficult to distinguish from very heavy atomic nuclei. A strange star could sit thousands of light years away looking, at first glance, rather like an ordinary neutron star. The problem is therefore not simply finding something strange. Physicists have to work out which measurable properties would be difficult for ordinary nuclear matter to reproduce, then search the universe for objects that show those properties consistently. That makes the hunt for strange matter a little like trying to identify what is inside a sealed box by weighing the box, shaking it, listening to the sound, watching how it moves when pushed, and hoping whatever is inside eventually does something distinctive enough to reveal itself. The most direct evidence would be the simplest conceptually. Find a piece of stable strange matter itself. A strangelet passing through a detector would give researchers the opportunity to measure properties such as its mass, electric charge, speed, and interaction with ordinary material. Strangelets are expected in many models to have an unusual relationship between mass and charge compared with ordinary atomic nuclei. A normal nucleus becomes increasingly positively charged as its proton number increases. A strangelet can contain a large amount of matter while carrying relatively little electric charge, because the charges of up, down, and strange quarks partly balance one another. If a detector found a compact object with the mass of a very heavy nucleus but far less charge than any ordinary isotope should possess, that would immediately attract attention. It would not be enough to announce strange matter after one unusual signal, because experimental detectors occasionally encounter backgrounds, measurement errors, and rare conventional events. But a reproducible object with the right combination of properties would be extremely difficult to explain away. Cosmic ray experiments are one place to look because the galaxy is constantly sending energetic particles toward Earth. Most cosmic rays are familiar particles, including protons and atomic nuclei, but if violent compact star events produce strangelets, some of those fragments could join the cosmic ray population. A charged strangelet moving through a magnetic spectrometer would curve according to its charge and momentum. By combining that information with measurements of its speed, researchers could infer its mass. The interesting signature would be an object whose mass and charge simply do not belong anywhere on the ordinary nuclear chart. Space-based experiments have searched for such objects and have not found convincing evidence, which allows physicists to place limits on how common particular strangelet populations can be. This does not prove strangelets are absent from the universe. They might be rarer than the experiments can detect, heavier or lighter than the ranges being searched, destroyed during their journey through the galaxy, or never produced in the first place. Still, every unsuccessful search removes some of the easier hiding places. Ancient material offers another strategy because a detector does not necessarily have to be an electronic instrument built by humans. The surface of the moon has been exposed to particles from space for immense periods without the thick atmosphere, weather, oceans, and active surface recycling found on Earth. If stable charged strangelets have been arriving in the inner solar system, some might have become embedded in lunar material. Samples returned to Earth can therefore be examined for atoms or nuclear-sized objects with impossible mass and charge combinations. Searches of this kind have not produced a confirmed strange matter sample either. That absence matters because lunar soil has effectively spent a very long time collecting whatever the cosmic environment sends its way. If a theory predicts a generous rain of stable strangelets, the moon becomes an awkward place for them all to have avoided. Accelerator experiments provide a more controlled search. When heavy nuclei collide at enormous energies, they briefly create conditions in which quarks and gluons behave in ways that ordinary nuclei cannot sustain. Researchers can then examine the products for unusual clusters containing strangeness. The challenge is that a high-energy collision creates extremely hot matter, whereas stable strange matter is generally discussed as a cold or comparatively cold dense state. Making lots of strange quarks is not the same as assembling them into a stable strangelet. a collider may produce particles containing strange quarks in abundance without ever producing a droplet of absolutely stable strange matter. Experiments have searched anyway, because discovering even one convincing stable strangelet would settle a question that decades of theory have left open. So far, the strange quark has been easy to produce compared with the strangelet, which continues to demonstrate the frustrating difference between knowing the ingredients exist and knowing they can form the particular state you want. If no fragment arrives at a detector, the next possibility is to identify strange matter through the stars it might create. A hypothetical strange star can resemble a neutron star in many ways. Both can contain roughly stellar masses inside an object only about the size of a city. Both can rotate rapidly. Both can possess magnetic fields. Both can appear as pulsars. Both can participate in binary systems and mergers. Looking at a point of radiation in the sky and discovering that it is compact does not tell you whether its interior contains neutrons, a mixture of hadrons and quarks, or strange quark matter throughout most of the object. The useful differences appear when we measure how mass, size, deformation, cooling, vibration, and surface behavior relate to one another. Mass and radius are among the most obvious clues. Every proposed form of dense matter predicts a relationship between how massive a compact star can be and how large it should be. Matter that resists compression strongly produces one sequence of possible stars, while matter that compresses more easily produces another. Strange quark matter adds the special possibility of self-binding. An ordinary neutron star is held together primarily by gravity. Reduce its mass far enough, and the structure changes because gravity is no longer strong enough to maintain the same dense configuration. An absolutely stable strange star, by contrast, could remain as a compact lump of self-bound quark matter, even at masses far below those normally associated with neutron stars. This creates one of the more interesting potential observational tests. Finding a genuinely compact object with an unusually low mass and properties requiring self-bound matter would be difficult to explain with a conventional neutron star. This does not mean every small compact object becomes proof of strange matter. Measuring stellar mass is difficult, measuring radius is difficult, and doing both accurately for the same object is more difficult still. Atmosphere models can change the radius inferred from thermal radiation. Distance uncertainties affect brightness estimates. Magnetic fields alter the spectrum. Hotspots on the surface can make the object look different depending on viewing angle and rotation. Theoretical descriptions of ordinary neutron star matter also produce a range of possible radii. An interesting measurement therefore has to survive a rather long conversation between observers and theorists before anyone can decide that conventional matter is genuinely in trouble. The heaviest compact stars provide a different test. Whatever matter exists in their cores must generate enough pressure to resist gravitational collapse. Observations of neutron stars with masses around twice the mass of the Sun already impose a strict requirement on dense matter models. Some early simple descriptions of quark matter had difficulty supporting such heavy stars because the material was too easy to compress. That once encouraged the argument that very massive neutron stars might rule out large quark cores. The situation is no longer so simple. Strong interactions and quark pairing can make quark matter sufficiently resistant to compression for strange star models to support heavy compact objects as well. A heavy pulsar therefore cannot by itself distinguish strange matter from nuclear matter. Instead, mass has become one piece of a larger set of constraints that every serious strange matter model must satisfy. Radius measurements add another piece. Telescopes observing X-rays from rotating neutron stars can use changes in brightness as hot regions move across the surface. Strong gravity bends the paths of the X-rays, allowing parts of the far side of the star to remain visible. By modelling the pulse shape, researchers can constrain the star's mass and radius. These observations are enormously valuable for dense matter physics, but they do not operate like an internal scanner. Several different equations of state can produce stars with similar masses and radii. A strange star model can fit some measurements, but so can various nuclear and hybrid star models. The goal is therefore to obtain enough accurate measurements across stars of different masses that the overall pattern begins favouring one family of internal structures over the others. Binary mergers give us another way to squeeze information from objects that refuse to reveal their interiors quietly. When two compact stars orbit one another, each star's gravity distorts the other. A very compressible star deforms more easily. A more compact star generally deforms less. This response is called tidal deformability, and it affects the gravitational waves emitted during the final stages of the inspiral. Detectors on Earth can measure those waves and place constraints on how deformable the stars were before they collided. Because deformability depends on the equation of state, gravitational waves provide a new route into the dense core without requiring light to escape from it. Strange stars can have tidal properties different from those of ordinary neutron stars, particularly in unusual mass ranges. The most revealing case could involve a compact star substantially lighter than the neutron stars normally produced by stellar collapse. A low-mass object made from ordinary neutron-rich matter and a low-mass self-bound strange star would respond very differently to tidal forces because their internal structures would be fundamentally different. If gravitational wave detectors eventually observe a binary containing such a low-mass compact object and measure its tidal deformability accurately, the result could become a powerful test of the strange star hypothesis. The difficult part is finding the right system. Nature has not arranged compact binaries according to the priorities of dense matter researchers. The collision itself can reveal information unavailable during the slow inspiral. When two neutron stars merge, density and temperature rise dramatically, and the combined object begins oscillating violently. If a transition to quark matter occurs, it can change the stiffness of the core, the rotation of the remnant, and the frequencies of the gravitational waves emitted after contact. A sufficiently strong phase transition might therefore leave characteristic features in the post-merger signal. Future gravitational wave observatories are expected to become much better at measuring this part of the event, which is currently more difficult than detecting the inspiral. A clear signature of a phase transition would be enormously important, but even that would not immediately establish strange matter. A transition from hadronic matter to some form of deconfined quark matter does not tell us automatically that the quark phase contains enough strange quarks to be absolutely stable. Detecting quark matter and proving the full strange matter hypothesis are related goals, not identical ones. The aftermath of a merger can supply electromagnetic clues as well. Material thrown outward during neutron star collisions produces heavy elements and powers a glowing transient. The amount and composition of the ejector depend on the properties of the colliding stars and the lifetime of the remnant. If strange stars collide, their ejected material and subsequent conversion processes could differ from those of ordinary neutron stars. Researchers have proposed possible differences in the light produced by such events, their neutrino emission, and the matter left behind. The problem is uniqueness. Merger signals depend on many factors, including the masses of the stars, their spins, the nuclear equation of state, neutrino interactions, magnetic fields, and the geometry of the collision. A strange matter explanation has to do more than reproduce an unusual burst. It has to reproduce something that the alternatives cannot reproduce just as well. Cooling has long offered another possible window. A newly formed compact star begins extremely hot and gradually loses energy. During much of its early evolution, neutrinos produced in the dense interior carry enormous amounts of energy away. Later, radiation from the surface becomes more important to what astronomers observe. Which particles exist in the core determines which neutrino-producing reactions are possible and how efficiently they operate. If quarks are present, new cooling channels may become available. If the quarks form paired superconducting states, some of those channels can be strongly suppressed. Strange quarks can influence the reaction network further. In principle, a strange star could therefore cool along a different path from an ordinary neutron star. In practice, compact star cooling is complicated enough to prevent one cold star from becoming an immediate strange matter announcement. Neutron superfluidity, proton superconductivity, magnetic fields, crust composition, stellar mass, envelope chemistry, and uncertain nuclear reactions all affect thermal evolution. Different internal models can produce overlapping cooling curves. A pattern observed across many stars of different ages is more useful than one peculiar object. If ordinary nuclear physics repeatedly failed to explain a population while a strange matter model predicted the temperatures naturally, the case would strengthen. Until then, cooling remains evidence that can support a picture rather than a signature that uniquely identifies it. The surface of a strange star may offer clues, because self-bound quark matter can end differently from gravitationally bound neutron star material. Depending on the detailed phase, the quark surface may possess a strong electric field and support a thin layer of ordinary matter above it. Some theoretical strange stars can carry a conventional crust separated from the quark matter by an electrostatic gap, while other possibilities involve a more exposed quark surface. Thermal radiation emerging from such an object could differ from that of a normal neutron star atmosphere. There have been proposals involving unusual spectral features, high surface binding, and different behavior of bursts. Yet the surface is precisely where astrophysics adds many complications. Magnetic atmospheres, condensed surfaces, uncertain chemical composition, and temperature variations can imitate unusual spectra. What appears to be evidence for exotic matter can sometimes turn out to be evidence that the surface model was too simple. Rotation supplies another collection of possible tests. Pulsars can rotate hundreds of times each second, and any realistic model of a compact star has to remain stable at the observed frequencies. Internal viscosity determines whether certain oscillations grow or are damped. One important family of oscillations is driven by rotation and can emit gravitational waves. Quark matter has different viscous properties from hadronic matter, and strange quark reactions can strongly influence how those oscillations are damped. This means the observed combination of stellar temperature and spin frequency can potentially constrain quark matter models. A strange star that should become unstable at a particular rotation rate but is observed spinning happily above it would create a problem for that model. Conversely, a population boundary matching a distinctive strange matter prediction could become supporting evidence. Pulsar glitches are sometimes mentioned as another clue. A glitch is a sudden small increase in the rotation rate of a pulsar. Ordinary neutron star models explain these events through interactions between superfluid components and the crust, although many details remain under active study. Strange stars may have different crusts and different internal rotational reservoirs, so their glitch behavior could differ. The difficulty is that strange star models are flexible enough to include structures capable of producing glitch-like events. The mere existence of glitches, therefore, does not rule strange stars in or out. As with so many other proposed signatures, the useful information lies in precise patterns rather than the simple presence of the phenomenon. An especially dramatic possibility would be observing the conversion of a neutron star into a strange star. If strange quark matter is absolutely stable and a suitable seed forms in dense nuclear matter, a conversion front could move through the star. The rearrangement might release a large amount of energy through neutrinos, heat, motion, or changes in the star's structure. Researchers have proposed connections between such transitions and energetic astronomical transients. One might imagine this providing the perfect signal. A normal neutron star exists. Something sudden happens, and afterward its properties match a strange star. Unfortunately, observing all three stages well enough to establish the interpretation would be extremely difficult. Stars undergo violent events for many reasons. Magnetic fields can produce powerful flares, accretion can trigger bursts, collapses and mergers release enormous energies. An unexplained flash does not tell us which microscopic particles were rearranged deep inside the source. A convincing conversion event would need several pieces to line up. There might be a sudden release of energy with a characteristic neutrino or gravitational wave signal, followed by a measurable change in the star's radius, rotation, cooling, or other bulk property. Even then, physicists would need to exclude alternative phase transitions and conventional stellar mechanisms. The standard of evidence would be high because the conclusion would be extraordinary. This is not excessive caution. It is exactly what prevents an interesting unexplained event from becoming an imaginary discovery. The strongest astrophysical evidence may therefore come not from one spectacular signal, but from several independent measurements converging on the same answer. Suppose compact star mass and radius measurements began favouring a self-bound sequence. Suppose low-mass compact objects appeared with radii that ordinary neutron star matter could not support. Suppose their tidal deformabilities match the strange star prediction. Suppose their cooling and rotational behaviour were also consistent with quark matter. Suppose merger observations showed phase transition features at pressures matching the same equation of state. None of those observations alone might prove strange matter, but together they would make the alternative explanations increasingly uncomfortable. Science often identifies unseen things this way. We did not need to hold a black hole in a laboratory to become confident black holes exist. Multiple independent observations eventually left little room for anything else. Even such a case would still leave one subtle question. Demonstrating that a star contains deconfined quark matter is not exactly the same as demonstrating that strange quark matter is the absolute ground state of strongly interacting matter. A hybrid star can contain a quark core maintained by enormous pressure, while remaining ordinary nuclear matter farther out. If the star were somehow disassembled, the quark phase might not survive. A genuine strange star under the traditional hypothesis would contain self-bound strange quark matter, capable of existing without that external pressure. Observations must therefore distinguish not just neutron stars from quark-containing stars, but pressure-supported quark phases from absolutely stable strange matter. That is a much harder standard. This is why an actual strangelet remains so attractive. A stable strangelet found far from neutron star pressure would directly demonstrate that a finite piece of strange quark matter can survive on its own. If its composition could be established and its properties match the predicted three-flavor state, the evidence would be far less dependent on interpreting distant stellar interiors. A strangelet would be strange matter arriving at our doorstep rather than asking us to infer it through gravity. It would not necessarily settle every detail of bulk stability immediately, because finite size effects still matter, but it would transform the subject overnight. There may be another astrophysical route almost as striking. If astronomers discovered an extremely low-mass compact object that was far too dense to be an ordinary planet, white dwarf or conventional neutron star, self-bound matter would become a compelling explanation. Ordinary neutron stars cannot simply be scaled downward indefinitely while retaining the same compact structure because gravity is essential to compressing their nuclear matter. Strange matter, if self-bound by the strong interaction, can in principle remain compact at much lower masses. Such objects have sometimes been described as strange quark planets, or low-mass strange stars. Measuring both their mass and tidal response could provide a particularly clean distinction, because ordinary and self-bound matter behave very differently in that regime. The problem, once again, is finding one and proving what it is. A compact object with an unusual inferred mass could be affected by errors in the binary model, inclination, distance, or interpretation of the signal. If gravitational waves reveal the object's tidal response directly, the argument becomes much stronger. Future detectors may therefore test parts of the strange matter hypothesis that current observations cannot reach, not by staring more closely at a typical neutron star, but by finding objects in regions of mass where the competing models stop resembling one another. This gives physicists a useful strategy. Do not search only where strange stars and neutron stars look similar. Search where their predictions pull apart. Extremely low-mass self-bound objects are one example. Precise merger oscillations may be another. Particular combinations of mass, radius, and tidal deformability can narrow the possibilities. Direct strangelet searches cover an entirely different scale. Lunar samples test accumulated cosmic exposure. Cosmic ray instruments test particles arriving now. Accelerator experiments test whether exotic quark clusters can be produced under controlled conditions. Each method attacks the hypothesis from a different direction. A genuine discovery would probably be followed by an enormous amount of skepticism, and that would be healthy. If a cosmic ray experiment reported a possible strangelet, another detector would need to confirm it. Researchers would examine whether an unusual ordinary nucleus could mimic the signal. Instrument calibration would be checked repeatedly. If a compact star appeared to have the properties expected from a strange star, alternative equations of state would be tested against it. The measurement would be repeated using different methods. Strange matter has been discussed for decades, and a discovery important enough to change our understanding of nuclear stability would require evidence strong enough to survive decades more. At the moment, that evidence has not arrived. We have compact stars whose properties constrain dense matter strongly, but none has been universally identified as a strange star. We have increasingly sensitive gravitational wave observations, but no signal has uniquely established stable strange quark matter. We have searches for strangelets in cosmic rays and ancient material, but no confirmed specimen. We have heavy ion experiments producing matter rich in quarks and strangeness, but no accepted stable strangelet emerging from them. The hypothesis remains alive not because evidence has already proved it, but because the allowed physics has not yet closed the door, and because astrophysical observations continue approaching the precision needed to test more of its predictions. That situation is more interesting than it may sound. Strange matter lives in a narrowing space between theory and observation. Every new massive pulsar asks whether the proposed material can support enough weight. Every improved radius measurement tests how compressible it can be. Every neutron-star merger probes its tidal behavior. Every strangelet search limits how much of it can be wandering through the galaxy. A hypothesis that once lived mostly in calculations is increasingly surrounded by measurements. Eventually one of two broad things may happen. Observations could keep tightening until no realistic version of absolutely stable strange matter fits everything we know, leaving strange quarks important in particle physics, but denying them the role of building a stable bulk phase. Or several independent signals could begin pointing in the opposite direction, toward compact objects that behave as though their matter is self-bound, phase transitions that suggest deconfined quarks, and perhaps one day a strangelet whose mass and charge refuse every ordinary explanation. Either outcome would teach us something important, because the question has never really been about finding an exotic substance, merely because exotic substances are entertaining. It is about discovering how the strong interaction organizes matter when density is pushed to its limit. If strange matter exists, it would tell us that the protons and neutrons making up almost everything familiar are not the only durable way quarks can organize themselves. If it does not, we would learn where and why the strong interaction prevents that alternative. The search, therefore, leads beyond detectors and neutron stars toward a much larger consequence, because deciding whether strange matter exists changes what we can say about the kinds of material the universe is capable of building, where that material might have survived since the earliest cosmic epochs, and whether some objects we currently call neutron stars have been hiding an entirely different identity. After following strange matter from ordinary atoms into neutron stars, down through protons and neutrons, and finally into a possible sea of up, down, and strange quarks, we are left with a question much larger than the material itself. Suppose some version of the strange matter hypothesis is correct. Suppose nature really can assemble a stable form of matter in which strange quarks are not temporary particles, but permanent members of a bulk material. What would that actually change about our picture of the universe? The first answer is surprisingly simple. Most of the universe we see would continue behaving exactly as it does now. The chair beneath you would not change. The Earth would remain made mostly from ordinary atoms. Stars like the Sun would continue burning hydrogen into heavier elements. Planets would continue forming from ordinary nuclei, and chemistry would still operate using electrons arranged around atomic nuclei. Strange matter would not make the world we already understand suddenly incorrect. What it would change is our understanding of how complete that world is. We would learn that protons and neutrons are not necessarily the final stable arrangement available to the quarks inside them, and that the matter making up almost everything familiar may represent one long-lived form among several possible forms of strongly interacting matter. That would be a major shift because ordinary nuclear matter currently sits at the foundation of almost every object we encounter. Atoms are built around nuclei are built from protons and neutrons are built from quarks. We usually tell that story as though reaching the quarks means we have reached the ingredients, and the rest is simply a question of how those ingredients are combined. Strange matter would remind us that the combination matters just as much as the ingredients. The same up and down quarks that normally remain confined inside separate protons and neutrons could, under sufficiently extreme conditions, become part of a larger shared state. Add strange quarks to that state, and the energy balance may change again. If the resulting material were absolutely stable, then the most familiar arrangement of quarks in the visible universe would not necessarily be the deepest one available. This does not mean ordinary matter would be unstable in the everyday sense. A carbon nucleus that has survived inside a rock for billions of years is doing perfectly well. The transition into strange matter, if such a lower energy state exists, would require conditions and microscopic processes that ordinary material does not normally experience. The important change would be conceptual. Physicists would have to distinguish between matter that is stable, because it occupies the absolute lowest available energy state, and matter that is stable, because the route to anything lower is extraordinarily difficult. Ordinary nuclei could belong to the second category, while remaining effectively permanent on any timescale relevant to life, planets, and normal stars. The consequences would become much more visible in compact objects. Neutron stars are already among the most extreme laboratories in the universe, but if strange matter is stable, some objects currently classified as neutron stars could have a very different internal identity. A conventional neutron star is supported against gravity by the properties of extremely dense nuclear matter. A strange star in the traditional picture would contain self-bound quark matter made from up, down, and strange quarks. Gravity would still shape the object and become crucial for a star with roughly stellar mass, but the underlying material would possess its own strong binding. Two compact stars could therefore have similar masses and similar dimensions, while being built according to very different microscopic rules. This would complicate the simple picture in which every collapsed stellar core either becomes a neutron star or continues collapsing into a black hole. There might instead be several possible endpoints. Some stars could leave ordinary neutron stars. Others might contain quark matter only in their deepest cores while retaining nuclear matter farther out. Under the strongest version of the strange matter hypothesis, some could eventually become strange stars containing strange quark matter through most of their interiors. The result would be a population of compact objects that look related from a distance but differ profoundly beneath their surfaces. How a strange star forms would then become an important part of stellar evolution. One possibility begins with an ordinary neutron star. As the star is born or later becomes denser, a sufficiently compressed region in the center could enter a deconfined quark state. Weak interactions could then produce strange quarks until the material approached its preferred composition. If strange matter were lower in energy than the surrounding nuclear matter, the new phase could grow. Instead of remaining a small core, it might convert more of the star. The process has been modelled as a conversion front moving through dense matter, with deconfinement first changing the organisation of the quarks and weak reactions, then adjusting their flavours. The details would matter enormously. A rapid conversion and a slow conversion would release and transport energy differently. Neutrinos could carry away part of the energy. The star could contract as its internal structure changed. Rotation might be affected. Heating could alter the surface emission. Under some models, the transformation could contribute to an energetic astrophysical event. None of these proposed signals is unique enough at present to let us point to a particular burst in the sky and confidently announce that a neutron star has become strange. But the possibility would add another mechanism to the already complicated lives of compact stars. It would also change how we interpret the death of massive stars. When a stellar core collapses, the object that emerges is born at extreme temperature and density, and then cools over time. If strange matter can form during that process, the earliest moments of a compact star could involve a sequence of transitions, rather than the simple creation of a neutron-rich object that then gradually loses heat. A star might begin in one phase, develop a quark core as conditions change, and later undergo further rearrangement as it cools, and its internal particle populations reach equilibrium. The final object we observe millions of years later could therefore hide a complicated history that happened during its first seconds, minutes, or years. Binary systems would make the story even more interesting. Compact stars often orbit companions, and some pairs eventually spiral together because they lose orbital energy through gravitational radiation. If strange stars exist, nature could produce several kinds of mergers. Two ordinary neutron stars could collide. A neutron star could collide with a strange star. Two strange stars could merge. Each combination would place dense matter under enormous stress while producing gravitational waves, neutrinos, and material ejected into space. The most tempting assumption is that a strange star merger would produce an unmistakably strange signal. Reality may be less cooperative. The bulk motion of compact stars is governed strongly by their masses, sizes, and gravitational fields, and different microscopic equations of state can sometimes produce similar large-scale behavior. Simulations have shown that some strange star merger signals may follow relationships resembling those found for neutron-star mergers. This means the universe might contain strange stars without every gravitational wave detector immediately noticing the difference. Researchers would have to search for subtler combinations of features, perhaps in the post-merger oscillations, the amount of material ejected, or the behavior of unusually low-mass self-bound objects. The ejected material would be especially important because it offers a route for strange matter to leave the star. If a strange star is disrupted during a collision, pieces of strange quark matter might be torn away. Large fragments could break into smaller fragments as they interact and cool. Some might become strangelets capable of travelling through the galaxy. If that happens often enough, and if the fragments remain stable, strange matter would no longer be confined to compact objects. Tiny pieces could wander through interstellar space as an unusual component of cosmic radiation. That would connect events involving objects the size of cities with particles small enough to pass through a detector near Earth. A strangelet recorded in a cosmic ray experiment might ultimately have been produced when two compact stars collided thousands or millions of years earlier. Its mass and electric charge could preserve information about the phase of quark matter from which it came. In that sense, the detector would not merely have found an exotic particle, it would have received a physical sample from the interior of one of the densest objects in the universe. There is also a more ancient possibility. Strange matter may not need stars to create it at all. Very early in cosmic history, the universe was far hotter and denser than it is today. Quarks and gluons existed in conditions where ordinary protons and neutrons had not yet become the dominant form of matter. As the universe expanded and cooled, the material passed into the hadronic world from which later atomic nuclei emerged. If that early transition allowed dense regions of quark matter to become trapped, and if strange quark matter were sufficiently stable, some quark nuggets might have survived. This suggestion has been studied since the early development of the strange matter hypothesis. The basic idea is that a phase transition in the young universe might have concentrated part of the available quark material into dense droplets. If the droplets were stable enough and large enough to survive evaporation, collisions and other early cosmic processes, relics could remain today. They would be incredibly old objects, older than stars, planets, and almost every structure now visible in the sky. Such relics have sometimes been considered as possible contributors to dark matter. This is an intriguing connection, but it needs especially careful wording because strange quark nuggets are not an established explanation for dark matter. We know from astronomical observations that galaxies and galaxy clusters behave as though they contain far more gravitating matter than the ordinary luminous material we can see. The identity of that dark matter remains uncertain. Compact quark nuggets have been explored as one candidate among a very large collection of possibilities. The attraction of the idea is easy to understand. A sufficiently dense quark nugget could contain enormous mass in a very small volume while interacting with ordinary matter differently from normal atoms. If a population of such nuggets formed early enough, it could contribute gravitationally to later cosmic structure. Instead of requiring dark matter to consist entirely of the completely new elementary particle, part of the missing mass could in principle be tied to an unusual phase of quarks that are already part of known particle physics. The difficulties are just as important as the attraction. Any proposed dark matter population has to satisfy a large collection of astronomical and cosmological constraints. There cannot be so many interacting objects that they produce effects we would already have noticed. Their formation must be compatible with the history of the early universe. They must survive long enough. Their collisions with stars, planets, gas and radiation must not violate observations. They also have to reproduce the gravitational behavior attributed to dark matter across very different scales. Saying that quark nuggets could be dark does not complete any of those tasks. Even if strange matter contributes nothing significant to dark matter, primordial nuggets would still be scientifically remarkable. Finding one would provide information about conditions in the universe when it was only a tiny fraction of its current age. Most matter from that period has been transformed repeatedly. Quarks became hadrons, nuclei formed, atoms appeared, stars processed elements, and stellar explosions scattered those elements into later generations of stars and planets. A surviving quark nugget would be a relic from before much of that history took place. There is another cosmic consequence that follows if stable strangelets are common. They could interact with neutron stars. A strangelet captured by a neutron star might sink into its dense interior. If the strangelet were absolutely stable, and if the surrounding nuclear matter could convert efficiently once contact occurred under those enormous pressures, it might provide a seed for transforming the star. Under that scenario, the abundance of strangelets and the abundance of strange stars become connected. A galaxy filled with stable strangelets might gradually convert susceptible neutron stars. This produces an unusual form of astronomical feedback. Strange stars could collide and release strangelets. Those strangelets could travel through the galaxy. Some could encounter other compact stars and potentially help convert them. If every step in that chain were efficient, strange stars might become increasingly common over cosmic time. The idea has sometimes led to arguments that either most neutron stars would eventually become strange stars, or stable strangelets must be rare enough that conversion does not happen frequently. The problem is that several uncertain pieces sit inside that argument. We do not know that strange stars exist. We do not know how many strangelets a collision would eject. We do not know how many fragments survive propagation. We do not know how efficiently they would be captured by compact stars, and we do not know exactly how a seed would behave after entering dense nuclear matter. The chain is useful because it connects different predictions, but it should not be confused with an established cycle occurring throughout the galaxy. If strange matter were confirmed, the consequences for particle physics would be just as important as the consequences for astronomy. The strong interaction is described by quantum chromodynamics, and strange matter would give us direct evidence about how that theory organises matter in the high density and relatively low temperature regime. That region is difficult to calculate and difficult to reproduce experimentally. We can create extremely hot quark matter in particle collisions, but a cold self-bound sample containing up, down and strange quarks would explore a very different part of the theory. This would help map what physicists call the phase structure of strongly interacting matter. Just as water has different phases depending on pressure and temperature, quark and nuclear matter may support multiple phases depending on density, temperature, composition and other conditions. We already know ordinary nuclei occupy one region of this landscape, and hot quark-gluon plasma occupies another. Neutron star interiors potentially explore the dense cold region, between familiar nuclear matter and the clean theoretical limit reached only at far greater densities. Confirmed strange matter would place a major landmark in that poorly mapped territory. It could also teach us about quark pairing. Dense quarks may organise into paired states analogous in broad spirit to superconducting states in other Fermion systems. With 3 quark flavours available, especially at very high density, particularly symmetric patterns become possible. If strange stars exist, their cooling, magnetic behaviour, rotational stability, and merger dynamics could contain information about which paired phase occupies their interiors. Strange matter would therefore not represent one simple substance, with one simple set of properties. It could open an entire field of dense phases distinguished by how quarks arrange and pair. That realization is important because scientific discoveries often make a subject larger rather than finishing it. Confirming strange matter would answer the question of whether stable 3-flavor quark material exists, but it would immediately create dozens of new questions. What is its exact composition at different pressures? How does its surface behave? Which quark pairing state dominates? Can electrons penetrate the material? How much ordinary crust can a strange star support? How does strange matter respond to magnetic fields? What happens when it is heated? How does it fracture, oscillate, cool and merge? What sizes of strangelets remain stable? How frequently are they produced? The first confirmed sample would not close the book. It would probably require several new books and an unfortunate number of conferences. Perhaps one of the most surprising consequences would concern the meaning of a neutron star itself. At the moment, the name is partly historical and partly descriptive. We know neutrons dominate large regions of these compact objects, but the deepest core remains uncertain. If observations eventually demonstrate that many compact stars are actually strange stars, then an entire astronomical population may have been named after material that does not dominate its interior. This would not be unprecedented. Scientific names often survive long after our understanding becomes more complicated. We still call sunrise sunrise even though the sun is not moving around Earth, in the way the word casually suggests. There may also be stars with intermediate identities. Some could contain ordinary nuclear matter throughout. Others could contain a deconfined quark core surrounded by nuclear layers. Others might consist mainly of self-bound strange matter. Distinguishing them would turn compact star astronomy into a kind of population study of the strong interaction. Instead of asking only how massive a star is or how fast it rotates, astronomers would be trying to classify which phase of fundamental matter occupies its interior. Future gravitational wave observations could become especially important for that task. As detectors become more sensitive, they should record more compact binary mergers and measure their properties with greater precision. The tidal deformation during inspiral tells us how compressible the stars are. The signal after merger can reveal oscillation frequencies and the lifetime of the remnant. Very low-mass compact objects could be particularly revealing because self-bound strange matter and gravitationally bound neutron star matter behave differently when gravity becomes less dominant. A compact object that remains extraordinarily dense at a mass where ordinary neutron star material should expand could become one of the stronger hints of self-binding. X-ray astronomy adds another set of measurements. Better determinations of compact star masses and radii can restrict which internal equations of state remain possible. Cooling observations can test how efficiently particles inside the star carry energy away. Pulsar timing can reveal changes in rotation with extraordinary precision. None of these methods guarantees a single decisive strange matter signature, but combining them can reduce the number of explanations capable of surviving all observations at once. This is likely how the question will be settled if no strangelet ever lands in a detector. We may gradually reach a point where one microscopic description explains compact star masses, radii, cooling, rotation, and merger behavior better than its alternatives. Strange matter could emerge not through one dramatic announcement, but through the accumulation of measurements that increasingly refuse to fit a purely nuclear picture. The opposite is equally possible. Observations could continue narrowing the allowed properties of dense matter until absolutely stable strange quark matter becomes increasingly difficult to accommodate. A negative answer would still matter. If strange matter turns out not to be stable, we would have learned something important about the strong interaction. We would know that the extra freedom provided by strange quarks is not enough to overcome their energetic cost under the relevant conditions, or that interactions between quarks prevent the three-flavor material from dropping below ordinary nuclear matter. Strange quarks could still appear inside neutron stars, hyperons, hot collisions, and temporary quark phases. They simply would not create the ultimate stable bulk state imagined by the strange matter hypothesis. That distinction brings us back to something easy to lose after talking about exotic stars and primordial nuggets. Strange quarks are real. Strange particles are real. Quark matter under extreme conditions is part of serious particle and nuclear physics. What remains uncertain is whether nature allows a sufficiently large mixture of up, down, and strange quarks to become self-bound and absolutely stable. Almost every dramatic cosmic consequence we have discussed depends on the answer to that one question. If the answer is yes, the universe may contain forms of matter separated by enormous differences in density, structure, and history. Ordinary atoms would dominate planets and normal stars because those environments favor atoms. Neutron-rich nuclear matter would appear where gravity compresses stellar remnants. Deconfined quark phases could emerge deeper still. Strange matter might occupy the lowest stable arrangement available to sufficiently large collections of quarks. Some compact stars could be made from it. Violent collisions could scatter fragments of it, and relic pieces might conceivably have survived from the early universe. If the answer is no, then nature has still taken us remarkably close to the edge. Strange quarks can exist, dense matter can reorganize, and protons and neutrons may lose their identities under extreme conditions without the final three-flavor state becoming absolutely stable. That would leave neutron star cores complicated, quark matter possible, and the strong interaction still capable of producing phases far removed from anything found on Earth. Either way, the question changes how we look at ordinary matter. Pick up almost any object nearby and it feels finished. Its atoms seem permanent, its nuclei secure, and the protons and neutrons inside them seem like dependable pieces that have been doing the same job since long before the object existed. Physics gives us a less comfortable but more interesting perspective. Matter has no obligation to stop reorganizing at the level most convenient for human experience. Change the pressure, temperature, and density enough, and structures that appear fundamental can become temporary arrangements. A proton is stable in the conditions around us, but it contains quarks. A neutron is comfortable inside many nuclei, but in free space it does not remain indefinitely. An atomic nucleus can survive for billions of years, yet at neutron star density, the very idea of an isolated nucleus disappears. Compress matter further and protons and neutrons themselves may stop being the right description. Allow strange quarks to join the resulting state, and perhaps another layer of organisation becomes possible. That is what makes strange matter worth thinking about even before anyone finds it. The hypothesis asks a very direct question about how much confidence we should place in familiar matter simply because it is familiar. The universe has already shown us solids, liquids, gases, plasmas, superconductors, superfluids, neutron-rich matter, and quark-gluon plasma. There is no particular reason to assume that our list of possible states is complete. So after all this talk of strange quarks, strangelets, strange stars, and matter that may have survived since the early universe, we can return to the much quieter place where we started. Wherever you are listening, the matter around you is almost certainly behaving in the ordinary way. Atoms are holding together, electrons are occupying their familiar states, protons and neutrons are keeping their quarks confined. Nothing nearby is showing any intention of becoming strange. The ordinary stability is not made less impressive by the possibility of something deeper. If anything, it becomes more interesting once we understand how many other arrangements the laws of physics may allow under different conditions. The universe can take the same fundamental ingredients and build a hydrogen atom, the center of a neutron star, a fleeting quark plasma, and perhaps a stable drop of matter containing strange quarks. The rules remain the same while the outcomes change completely. If you have stayed with me through this entire journey, I would love to know where you are listening from and whether strange matter now seems less strange than it did at the beginning. Perhaps the name still sounds as though it belongs in science fiction, but the idea behind it comes from a very practical question. When matter is compressed until atoms disappear, nuclei merge, and protons and neutrons can no longer keep their familiar identities, what arrangement do the quarks choose next? We do not yet know the final answer. That is not a disappointing place to finish. It means the question remains connected to observations that are happening now and experiments that can still surprise us. New compact star measurements, new gravitational wave events, more sensitive cosmic ray searches, and better calculations of dense quark matter can all change the limits of what we know. Perhaps strange matter will eventually become a confirmed part of the universe. Perhaps it will remain a beautiful possibility that nature never actually uses. Either result will tell us something fundamental about the particles inside every proton and neutron around us. For the moment, the safest conclusion is also the most interesting one. Ordinary matter is the form of matter we know best, not necessarily the only form nature can build. Somewhere inside the crushed remains of stars, or perhaps nowhere at all, quarks may have found another arrangement. Finding out whether they have is one of those questions that begins with something smaller than a proton and ends with the structure and history of the universe itself. If this quiet trip through strange matter has given your mind somewhere interesting to wander, you can leave the video a like and subscribe to Physics with William for more journeys through the parts of science that become stranger the closer we look. Wherever you are listening from, and whatever time it happens to be there, the ordinary atoms around you have managed to hold their familiar arrangement for another evening. We can leave the strange quarks to the neutron stars for now, and let the rest of the universe continue its experiments without us watching every second.